The Porsche 911 is built with unmatched precision and legendary craftsmanship. From raw aluminum sheets to hand-finished interiors, every stage of production combines cutting-edge robotics with skilled human expertise. Today, we go inside the factory to witness the birth of the 911 and reveal how this iconic sports car is engineered and perfected before it ever hits the road. Our journey begins not with steel or aluminum, but with legacy. Since 1964, the Porsche 911 has set the benchmark for what a sports car can be. Agile, luxurious, powerful, and above all, engineered to the most meticulous standards. The factory that produces this legendary vehicle has been refined and modernized over the years to accommodate new technologies, hybrid integrations, and greater levels of customization, all while preserving the artisanal heart of the brand. Before the first bolt is torqued or the first body panel is pressed, there is data. Every Porsche 911 is built to order, meaning that no two cars are truly identical. Customers choose from an enormous range of exterior colors, wheel types, interior trims, upholstery patterns, drive configurations, and optional performance packages. Each of these selections is encoded into a build sheet, which becomes the digital DNA of the vehicle. This build sheet is fed into Porsche's centralized manufacturing management system. From this point forward, each chassis will be tracked, scheduled, and updated in real time across every workstation in the plant. The first tangible phase of production begins with the body-in-white construction, which refers to the process of creating the raw, unpainted body shell of the car. In the Porsche 911 factory, the body is built primarily from aluminum and high-strength steel, a marriage of materials that balances rigidity with weight savings. Rolls of sheet aluminum are delivered to the plant and fed into massive hydraulic stamping presses, which operate with pressures exceeding 5,000 tons. These presses form the outer panels of the car, doors, fenders, roof skins, and hoods into their precise curvatures. Each stamping is inspected by laser measurement tools that ensure every contour conforms to Porsche SI's exact specifications, down to fractions of a millimeter. Once all the necessary stamped components are formed, they are sent to the body shop, a cavernous facility where man and machine work side by side. Here, more than 400 industrial robots perform the majority of the welding, riveting, and adhesive bonding. These robots move with uncanny grace and speed, precisely positioning panels and applying structural adhesives or welds with the consistency of a human heartbeat. However, not all tasks are left to automation. Certain weld seams and alignment tasks are still completed by hand, especially those in areas where absolute perfection is required for NVH performance, noise, vibration, and harshness, or where tolerances are too tight for robotic arms to operate without collision. The skeleton of the 911, now taking on its recognizable coupe shape, passes through a series of structural validation checks. Vision systems scan the entire body in white using 3D laser triangulation, capturing a high-resolution digital map of the vehicle geometry. This map is then cross-referenced with the CAD model to identify any deviations. If even a single hole is misaligned or a weld bead is out of tolerance, the vehicle is automatically removed from the line and reworked before proceeding. From the body shop, the chassis enters the paint shop, which is itself a marvel of process engineering. Here, the raw metal body is first subjected to a full chemical cleaning and pre-treatment cycle. It is submerged in a series of dip tanks containing degreasers and anti-corrosion agents, and then it undergoes electrocoating, an electrophoretic process in which an electrical current is passed through the body shell while immersed in a primer bath. This ensures that every crevice, seam, and channel within the structure is evenly coated for rust protection. Once primed, the body passes through a drying oven operating at temperatures of up to 180 degrees Celsius. After cooling, the body is transferred via overhead conveyor to the paint booth. Each booth is a climate-controlled, dust-free chamber where robotic arms, fitted with electrostatic spray heads, apply successive coats of base paint, metallic flakes, and clear lacquer. The electrostatic spray method ensures minimal overspray and maximum efficiency, as the charged paint particles are drawn to the grounded metal body like iron filings to a magnet. Porsche allows for an extraordinary range of exterior colors, and some bespoke configurations can require manual intervention. In these cases, highly trained paint technicians in full-body clean suits step into the booth to manually apply specialty finishes, such as pearlescent or matte paints using handheld spray guns. Between each paint layer, the body is baked and cooled, creating a hardened shell that is both visually flawless and highly durable. The finished result is a surface that must pass microscopic inspection under polarized light to ensure there are no inclusions, orange peel textures, or color mismatches. As the painted bodies emerge from the drying ovens and cool under carefully controlled humidity conditions, they are fitted with temporary protective films to prevent scratches during subsequent assembly stages. These painted shells are then placed onto autonomous guided vehicles, AGVs, that shuttle them silently and efficiently to the final assembly hall, where the true transformation from body to car begins. In parallel to body production and painting, a completely different but equally intricate process has been taking place: powertrain assembly, the heart of every Porsche. 911 is its engine, and this component is assembled in a separate, climate-controlled facility adjacent to the main plant. Whether it is a twin-turbocharged flat 6 or a naturally aspirated GT series engine, every unit begins with a bare block, precision machined from a solid billet of aluminum alloy. Each cylinder bore is honed to within microns of its target diameter, and oil channels are cleaned using ultrasonic pulses and compressed air. Engine assembly is a partly manual process performed by specialized technicians who are each responsible for a particular section of the engine. Crankshafts are balanced using laser-guided measurement tools before being seated into their main bearings. Pistons are installed with zero contact to the bore walls, often using air-cushioned insertion tools that prevent even microscopic abrasion. The timing assembly, turbochargers, camshafts, and intake plenums are all mounted with torque-controlled tools calibrated to within a fraction of a Newton meter. Every engine is subject to a dynamic test bench where it is fired up, run through a simulation of driving conditions, and monitored for vibration, oil pressure, thermal behavior, and exhaust output. Only after passing this test is it stamped with its serial number and released to the vehicle assembly line. As the fully painted and protected body shell glides into the final assembly hall on its autonomous guided vehicle, the environment around it becomes a symphony of motion, sound, and precision. This hall is the nexus of the Porsche 911's creation, where everything converges: chassis, drivetrain, interior, electrics, and finishing. The space is brightly lit, immaculately clean, and orchestrated down to the second. Here, automation doesn't replace craftsmanship, it supports it. Skilled technicians and robotic assistants work in tandem, each knowing their roles to an exacting degree. The very first step in this phase is the marriage process, one of the most significant moments in the entire build. This is where the engine, transmission, and rear suspension subassembly, known collectively as the drivetrain module, are bolted to the body. Unlike many front-engine cars, the Porsche 911's signature rear-mounted engine demands a specific approach to alignment and attachment. The powertrain arrives beneath the suspended body shell on a separate carrier, having been pre-assembled and tested in a different wing of the plant. Technicians first conduct a visual and digital verification of the mounting points on both the chassis and drivetrain module. Hydraulic lifts then lower the body shell in slow, controlled increments toward the powertrain unit. At a precise height, robotic torque arms automatically engage the mounting bolts at each corner of the assembly, securing the engine and suspension cradle to the vehicle's rear subframe with surgical precision. Torque specs are logged digitally in the system to ensure that every car meets identical standards. This point is symbolic and functional, the moment the 911 gains its heart. From here, the partially complete car progresses down the assembly line, where the front axle, steering rack, and brake assemblies are installed. These components, like the rear drivetrain, arrive as pre-assembled modules. Porsche's modular assembly system allows highly efficient integration of these parts without slowing the line. The braking system is one of the most advanced in the world, and depending on the configuration chosen by the customer, technicians may install standard steel rotors, larger vented discs, or the elite Porsche ceramic composite brakes. Each caliper is pre-bled and electronically matched to the ABS and stability systems that will later be programmed. As suspension components are torqued into place and the car sits on its wheels for the first time, it travels into the electrical systems installation zone. This is one of the most complex areas in the entire factory due to the sheer density of cabling, sensors, control units, and wiring harnesses that must be routed throughout the body. Unlike conventional vehicles, where looms are installed early, the 911's configuration-specific electronics require precise timing. A team of specialized technicians begins threading the main wiring harness through the firewall, under the dash cross member, along the floor channels, and into the trunk and engine compartments. Multiple electronic control units responsible for engine management, infotainment, lighting, climate control, adaptive suspension, and driver assistance systems are installed along the way. Each ECU is connected and tagged with an identifier, which is scanned into the system to track software compatibility and firmware updates later on. This process involves a blend of manual dexterity and robotic support. Certain harness connections are guided into position by human hands, while robotic arms press connectors into tight sockets with consistent pressure. The system is then subjected to an initial low-voltage power-on sequence to confirm basic circuit integrity. As the car continues down the line, it enters the interior assembly stage, where it truly begins to look and feel like a Porsche. Interior trim parts, such as dashboards, center consoles, seats, door panels, and headliners, are assembled in adjacent cleanroom environments. The level of customization offered for interiors is staggering. Multiple grades of leather, contrast stitching, carbon fiber inlays, Alcantara accents, and rare wood veneers are all possibilities. Each trim package is pre-selected and kitted into an interior build set specifically for the chassis number it will be installed into. The dashboard is one of the first interior components to be fitted. A robotic jig lifts and rotates the dash into the open body shell through the passenger side, where it is then fastened to the front firewall and A-pillar mounts. Once secure, technicians connect HVAC ducts, wiring looms, and install the infotainment screen and gauge cluster. The 911's trademark 5-dial instrument panel is precision calibrated using a laser alignment system to ensure readability and balance. Following this, the central tunnel is installed, anchoring the shifter mechanism, cup holders, and control switches in place. The seating units are next. These are hand-finished in a separate upholstery shop within the factory, where master stitchers work with hides sourced from Northern European cattle farms, chosen for their lower insect scarring due to colder climates. Each seat is sewn, padded, and assembled by hand. Once complete, they are lifted into the cabin using overhead manipulators, then bolted to their mounting rails. Power connections, for seat adjustment, ventilation, and memory functions are plugged in and tested on the spot. Following seating installation, door panels, headliners, sun visors, carpeting, and sound insulation materials are methodically added. All of this must be done with extreme care to avoid damage to visible surfaces. Each technician wears custom-fitted gloves and uses tools wrapped in soft plastics to ensure the integrity of every trim surface. As the cabin nears completion, a special quality station is activated where technicians test interior lighting, switchgear function, speaker outputs, and HVAC performance using a diagnostic tablet linked directly to the vehicle's control system. Meanwhile, the exterior finishing process runs in parallel. Pre-assembled elements such as side mirrors, window glass, lights, grills, badges, and bumpers are attached in stages. The front and rear bumpers, painted separately to ensure flawless color match, are fitted using a rail-guided alignment jig that positions each part within a millimeter of its target mounting point. Headlights and taillights are connected and auto-aligned using optical calibration equipment that verifies beam pattern and aim. Next comes the fluid fill stage, where the car receives its essential life fluids: engine oil, transmission fluid, brake fluid, coolant, and refrigerant. Each fluid is dispensed using digitally controlled nozzles that measure exact volumes and record fill data for traceability. The 911's flat 6 engine is particularly sensitive to oil quality and temperature, so the system pre-warms the oil before injection to avoid shocking the internal components. Once all fluids are added, a leak test is conducted using pressure sensors and ultrasonic detectors that can identify even the smallest leak before the vehicle progresses further. The moment the car rolls under its own power for the first time is known as initial startup. At this station, technicians power on the ignition and bring the engine to life. A thick hush falls over the work area as everyone listens intently for any anomalies. The car's onboard diagnostic system runs through a series of checks, monitoring oil pressure, coolant temperature, voltage levels, and sensor outputs. If the car passes this phase, it proceeds to a short drive loop within the factory called the roll test station. In the roll test, the car is placed on a chassis dynamometer, where it is effectively driven at various speeds while remaining stationary. This test simulates road conditions and allows technicians to check gear shifts, brake modulation, ABS function, stability control, steering responsiveness, and exhaust emissions. Sophisticated microphones and vibration sensors placed around the cabin and under the chassis detect unwanted noises or harmonics that might indicate misalignment or defective components. If everything checks out, the car moves to its final quality inspection phase. Here, white-gloved inspectors examine every visible surface of the vehicle under high-intensity lighting in a booth designed to mimic daylight. They look for paint flaws, panel gaps, alignment inconsistencies, and trim defects. Even a single misaligned badge or a fiber of dust under the clear coat can trigger a corrective action. The interior is similarly scrutinized. Vents are tested, buttons are pressed. Leather is scanned for imperfections. As the freshly assembled Porsche 911 completes its final static inspection, it is now ready for the next critical phase: dynamic validation. This is where the vehicle leaves the controlled environment of the assembly hall and is put to the test in real-world conditions, albeit within the carefully designed confines of Porsche's own internal test facilities. Unlike mass-market vehicles that may rely solely on automated testing systems, the Porsche 911 undergoes an extensive series of physical evaluations driven by human specialists who are trained to detect even the subtlest inconsistencies in performance, feel, and response. The process begins with a water tightness test, sometimes referred to as the monsoon chamber. Each vehicle enters a sealed booth where it is subjected to a simulation of extreme weather. High-pressure jets of water are sprayed from multiple angles, replicating driving through torrential rain, deep puddles, and car washes. The water includes fluorescent dyes, invisible to the naked eye, which are later detected under UV light to identify any intrusion into the cabin or trunk spaces. After several minutes of intense soaking, the car is dried using warm air blowers and checked for leaks or dampness. If the vehicle passes, it is cleared for what many consider the most thrilling part of the production process, the road test. At Porsche's Zuffenhausen facility, a dedicated test track is built into the complex. This closed-loop circuit includes a range of surfaces, elevations, and cornering radii to evaluate every aspect of the 911's performance. Professional test drivers take each car through a series of maneuvers: rapid acceleration, hard braking, slalom turns, rough road surfaces, and steady-state cruising. They listen for abnormal vibrations, dashboard rattles, or drivetrain noise that might indicate improper assembly. Each steering input and suspension reaction is scrutinized. The driver is also watching for proper calibration of the stability management systems, throttle response, gear transitions, and the characteristic mechanical symphony of the 911's powertrain. During this phase, real-time telemetry is streamed from the car to a control center, where engineers monitor data points such as torque delivery, ABS performance, yaw rate, and fuel injection timing. Should any parameter deviate from specification, the car is immediately flagged for corrective adjustment and returned to the factory floor. Once the road test is complete and the car has passed all dynamic performance benchmarks, it is returned to the post-production area for final detailing and preparation. Here, the protective films that were applied after painting are carefully removed. These thin polyethylene sheets have safeguarded the car's painted surfaces throughout the entire assembly process. After their removal, highly trained detailing technicians begin what is often a several-hour procedure to bring the vehicle to showroom condition. Using dual-action polishes, microfiber cloths, and a specialized lineup of Porsche-approved polishes and waxes, they inspect and refine every panel to ensure depth of gloss and clarity of reflection. The interior receives equal attention. Surfaces are dusted, vacuumed, and wiped with non-abrasive cleaners. Fingerprints are removed from touchscreen interfaces, leather is conditioned, and carpets are brushed into uniform directionality. If the car has a convertible top, it is cycled several times to confirm fluid movement and complete sealing. Final torque checks are conducted on exterior trim, wheel bolts, and undercarriage elements. Any last-minute adjustments, such as wheel alignment tweaks or software calibration, are made during this phase. After detailing, the car is moved into the certification bay. Here, its full build record, component scan history, torque log, quality inspection reports, and road test results are compiled into a permanent digital archive linked to the car's VIN. This digital log will remain with the car for the rest of its life and can be accessed by Porsche service centers worldwide. A final multi-point checklist is reviewed by a senior quality engineer. This is a manual review signed off in person, reinforcing the company's philosophy that human craftsmanship and responsibility must coexist with digital precision. Once this final sign-off is completed, the car receives its protective packaging for transport. Soft foam inserts are placed between the tires and the wheel wells to prevent compression damage during shipping. Cloth covers are fitted over the seats, steering wheel, and center console to protect against handling marks. A thick vinyl exterior wrap is then applied over the entire painted surface, including the hood, roof, fenders, and doors. The car is now ready to leave Zuffenhausen, but its journey is only beginning. Porsche's global distribution network is meticulously coordinated from a central logistics hub located on the factory grounds. Each finished vehicle is scanned into the logistics system and assigned to a specific transport route. For cars bound to European dealerships, Overland transport by custom-fitted enclosed car carriers is the norm. These trucks are climate-controlled, padded, and outfitted with individual restraint systems to prevent shifting in transit. For overseas markets, including North America, Asia, and the Middle East, the cars are transferred to the port of Bremerhaven, one of the largest automotive export hubs in Europe. En route, they travel by dedicated rail cars equipped with vibration-dampening suspension systems. Each car's location, condition, and shipment status is monitored using GPS trackers and RFID tags embedded in the vehicle's packaging. Upon arrival at the port, the vehicles are unloaded into secure storage lots, awaiting roll-on, roll-off vessel boarding. Porsche does not allow external drivers to handle the vehicles. Instead, factory-certified personnel drive each 911 onto the ship's internal decks, where they are secured using specialized harness systems. The shipping containers are climate monitored, and their humidity levels are controlled to prevent corrosion or material degradation during the voyage. Some regions with extremely sensitive climates, such as tropical zones or high humidity areas, require an additional layer of desiccant packaging and underbody protection. Once the cars arrive in their destination country, they are typically routed through a regional Porsche distribution center. These centers conduct a pre-delivery inspection or PDI. During this process, shipping materials are removed, fluid levels are rechecked, tire pressures are set to local spec, and country-specific features such as local language infotainment systems, navigation maps, and compliance labels are configured. The battery, which may have been put in shipping mode during transit, is recharged and tested. Only once the car clears this PDI is it finally released to the dealership. At the dealership level, the car undergoes one final cosmetic inspection before being presented to the customer. If a customer has ordered their 911 through Porsche's exclusive manufacturer program, this delivery often includes a ceremonial handover in a private lounge, with factory personnel available to walk through every detail of the vehicle's features. In some cases, particularly in Europe, customers can even take delivery at the factory itself, where their car is unveiled in a glass-walled rotunda with dramatic lighting, followed by a first drive on scenic roads around Stuttgart. Yet even after delivery, the role of the factory is not quite over. Thanks to Porsche's connected car architecture, many vehicles are capable of over-the-air updates that improve performance, add new features, or correct bugs discovered in the field. Data collected during actual driving, such as engine behavior, brake wear, and climate control usage, is anonymized and fed back to Porsche's research and development teams to inform future designs and calibrations. It's a feedback loop that allows every Porsche built today to contribute to the improvement of the next generation. Meanwhile, back at Zuffenhausen, production continues. Every morning, a new batch of orders is passed into build sequences based on available component inventory, production capacity, and shipping schedules. Hundreds of thousands of individual parts must be delivered to the exact right station at the exact right time to maintain flow. This is made possible through a just-in-time logistics strategy, supported by automated material handling systems and a synchronized supplier network. Some high-value or rare components, such as carbon ceramic brake rotors or forged aluminum wheels, are flown in daily from satellite facilities or specialist subcontractors. The factory itself operates with a level of sustainability and energy efficiency that reflects the future of manufacturing. Solar panels line the roofs, producing a significant percentage of the plant's electricity. Rainwater harvesting systems supply grey water for cleaning and HVAC cooling. Waste heat from the paint ovens is recirculated to warm other parts of the facility, and zero waste policies ensure that unused materials are either recycled or repurposed. Even the autonomous transport carts that move parts and vehicles between stations run on battery power. coordinated by an AI-powered logistics brain that continuously optimizes paths and traffic flow. By the time a single Porsche 911 is completed and delivered to its owner, it has passed through the hands of more than 1,500 people, touched over 3,000 unique components, and been subjected to hundreds of quality checks and dozens of performance tests. Every detail, from the composition of its alloy wheels to the grain of its leather, has been examined, tested, and refined to deliver the unified experience that the 911 is known for. Inside the Zuffenhausen facility, what stands out most beyond the hum of machinery and gleam of painted panels is the harmonious integration of advanced automation with human craftsmanship. While much of the modern automotive world has shifted heavily toward fully robotic production lines, Porsche has taken a more balanced approach. It is this hybrid system, where intelligent machines handle precision tasks and highly trained specialists deliver the emotional and tactile elements, that makes the production of the 911 so uniquely effective and true to its heritage. To understand the depth of Porsche's production system, we need to go deeper into the factory automation architecture that supports every step of the process. Central to this is the Manufacturing Execution System, or MES. This digital control layer connects every workstation, tool, robot, and technician across the plant in real time. From the moment a customer's order is locked in, a virtual avatar of that specific car is created within the MES. This avatar tracks everything: colors, materials, powertrain choices, region-specific requirements, and optional extras, and constantly relays this data to the precise equipment or technician that will handle each part of the build. In the chassis assembly line, for example, if a customer has ordered rear-wheel steering and adaptive PASM suspension, the MES sends signals to the automated picking system to retrieve the correct components. A robotic arm pulls these from storage bins, places them into a bin or cart customized for that vehicle, and tags it with the car's digital signature. The cart then travels on a guided track to meet the body shell exactly as it arrives at the workstation. At no point is there ambiguity or lag. Everything is orchestrated by this unseen digital conductor that ensures every worker and every robot knows exactly what to do for every unique build. Beyond simple part logistics, Porsche's MES also controls robot behavior, torque tools, and environmental systems. Take the example of robotic arms applying sealant to the underbody and joints of the car. These robots receive precise instructions on bead width, viscosity compensation, path mapping, and cure time, all tailored to the ambient humidity and temperature at that exact moment. If conditions drift even slightly out of tolerance, the system adjusts on the fly. If a deviation is too great, the system pauses the robot and calls for human review. This level of responsiveness ensures not only uniform quality, but a kind of built-in vigilance that prevents minor errors from becoming major issues downstream. Nowhere is this marriage of automation and craftsmanship more evident than in Porsche's exclusive manufacture department, a special division within the factory dedicated to bespoke customization. Here, human hands reign supreme. Customers who opt for this level of personalization can request everything from custom mixed exterior colors to leather-trimmed air vents, contrast-stitched seatbelts, or brushed aluminum door sills engraved with their name or family crest. These options cannot be installed by robots. They demand skilled labor, patience, and a deep understanding of materials. For instance, if a customer chooses deviated stitching in a rare color like Guards Red on a graphite interior, that thread is sourced separately, wound into bobbins, and installed on special industrial sewing machines operated only by master upholsterers. Each stitch line must be perfectly parallel and uniformly tensioned. The leather pieces are cut using high-frequency oscillating blades controlled by software, but the actual alignment and mounting onto trim pieces is done manually, using a keen eye and muscle memory developed over years of experience. Even more exclusive are options like natural wood inlays, which are created by slicing extremely thin veneers from selected timber, pressing them onto aluminum substrates, and hand finishing them with lacquer, polishing, and oiling processes. Because natural wood grains are unpredictable, no two trim sets are alike, and each must be evaluated for visual balance and grain orientation by an expert before being installed. Moving to another area of innovation, we find the powertrain production of the 911 continuing to evolve alongside the rest of the industry. While Porsche remained steadfast in its commitment to the internal combustion engine, particularly the legendary Flat 6, it has also begun preparing for a future that involves greater electrification. Already, hybrid-ready architectures are being integrated into the production lines, and new high-voltage testing bays have been built to accommodate future variants. The current engines are built in a separate but nearby facility that operates with a clean room-like atmosphere. Every engine builder works at a station equipped with digital torque wrenches, oil mist extractors, and real-time visual feedback displays. These displays show exploded diagrams of the current build, torque values required for each bolt, and any sequencing constraints. This allows even complex assemblies, such as the twin turbocharged air intake plenum or variable cam timing modules, to be installed with absolute accuracy. Each engine is assembled in a vertical build sequence, meaning it remains upright throughout the process to reduce the risk of contamination or misalignment. Oil galleries and cooling jackets are cleaned with pulsed air systems and inspected with endoscopic cameras before being sealed. Once complete, the engine is placed on a mobile test rig, where it undergoes a cold test cycle, rotated via electric motors without fuel ignition to measure resistance, internal pressure differentials, and sensor behavior. Only after passing this does it proceed to hot testing on a dynamic dyno bench. The dyno bench is a marvel in itself. Each engine is connected to a computer-controlled load cell and run through a simulated break-in process. Sensors record everything: oil pressure fluctuations, exhaust lambda values, detonation signatures, and even the sound frequency of valve operation. The engine is revved, held under load, cooled, and restarted multiple times. Only when it has performed flawlessly under all conditions is it released and stamped with a code that matches it permanently to a specific chassis. Returning to the factory floor, the final fit and finish phase is where Porsche's obsession with detail truly shines. One area of particular focus is panel alignment and gap consistency. Unlike volume manufacturers, where acceptable tolerances for panel gaps can vary by several millimeters, Porsche targets consistency within less than half a millimeter. Each door, hood, and trunk lid is mounted loosely at first, then adjusted using laser-guided tools and feeler gauges. Special brackets hold the panels in place while final torques are applied. This is not just for aesthetics. Precise gaps reduce wind noise, improve aerodynamics, and enhance door closing feel. Sound is another key dimension. Engineers at Porsche place heavy emphasis on acoustic tuning, not only of the engine and exhaust, but also of the cabin itself. During development, microphones are embedded in prototype vehicles and driven through tunnels, highways, and cobblestone streets to capture all forms of noise, resonance, drumming, creaks, and wind intrusion. The data is used to inform production processes such as body seam sealing, insulation placement, and even the thickness of laminated glass. Once in production, these same noise benchmarks are monitored. If a particular car emits even a slightly louder door rattle than expected, it is pulled for correction. Climate performance is also evaluated under extreme conditions. Select vehicles are placed inside thermal chambers that simulate environments from Arctic cold to desert heat. Inside, engineers test HVAC operation, defrost speed, material expansion behavior, and adhesive bonding under thermal stress. Porsche uses infrared cameras to study heat distribution inside the cabin and applies this information to optimize vent design and airflow management. Finally, we must acknowledge the human element, the thousands of workers and craftspeople who bring each 911 to life. At Zuffenhausen, training is rigorous. Every new technician undergoes months of apprenticeship, not just in tool use or station procedure, but in the philosophy of Porsche manufacturing. This includes historical education on past models, design language, customer expectations, and a deep respect for the badge each vehicle will wear. Quality auditors rotate through various departments, performing random checks, coaching less experienced colleagues, and updating work instructions when issues arise. Continuous improvement is part of the culture, and feedback loops from dealerships and customer surveys are studied and integrated into daily operations. It's not uncommon for production processes to be revised weekly, not because something went wrong, but because something could be done just a little better. Our journey begins deep within the steel supply and stamping operations, far from the glittering finish lines of final inspection. The G-Class starts life as a collection of raw, flat metal panels. These panels, primarily high-strength steel, are delivered to the facility in massive coils, which are unrolled and leveled before being fed into industrial press machines. These presses apply thousands of tons of pressure to shape the steel into the various foundational parts of the G-Class body, such as the floor pan, door skins, roof frame, and iconic flat body panels. The unibody shell is not used in the G-Class. Instead, it's built with a ladder frame chassis, a method more common in heavy-duty trucks. This makes the process both more rugged and more complex, requiring each piece to be perfectly formed to exact tolerances. Once the panels are pressed, laser-guided robotic arms trim and smooth the edges with astonishing precision. Each cut is planned digitally down to the 1/10 of a millimeter, ensuring uniformity across thousands of units. Now we move into the body in white phase, the initial stage of structural assembly. Here, the stamped panels are arranged into sub-assemblies. The floor pan, side frames, firewall, and roof supports are meticulously aligned on a series of jig fixtures. These large, articulated steel mounts hold each piece in perfect position for welding. But unlike many modern car factories where robot arms zip through spot welds in a blur, the G-Class body is largely welded by hand. Dozens of skilled technicians, each highly trained, wield welding torches in a choreographed dance of sparks and heat. More than 6,000 welds are performed on each body, reinforcing the vehicle's structural rigidity. As they go, workers constantly inspect joints visually and mechanically using go-no-go gauges to confirm tight fits and ensure that structural integrity is never compromised. The welding process is a symphony of patience and expertise. Welders must account for heat distortion, managing the order and location of each weld to maintain the geometric accuracy of the body. They use pneumatic clamps, steel rulers, and laser levels to ensure that the angles and lines of the body remain true. It is here that the G-Class's signature upright posture begins to take shape. Those vertical window frames, slab-sided doors, and angular corners that give the vehicle its commanding silhouette. They're all defined and locked into place during this early phase. Once the body is fully welded and structurally complete, it undergoes a process known as metal finishing. This is where skilled craftsmen examine every seam, edge, and panel for imperfections. Small hammers, abrasives, and filler tools are used to smooth out inconsistencies. The goal is to achieve a surface that will accept paint without a single visible ripple or deformity. The attention to detail here is extraordinary. What may seem like an invisible bump to the naked eye will be caught later by paint defects if not resolved. Technicians in this stage often use high-powered overhead lights and fingertip inspection techniques to feel for irregularities. And yes, they still do it by touch. Technology can detect misalignments, but it's the trained human hand that often finds the smallest flaws. Once the body in white has passed inspection, it is ready for paint preparation. But before any color is applied, the shell undergoes a rigorous cleaning process. It is first immersed in a series of chemical baths, alkaline cleaners, degreasers, and deionized water rinses that strip away all traces of oils, residues, or contaminants from the welding and finishing stages. Then it moves into the e-coating process. This is where the body shell is dipped into a giant electrocoating tank filled with anti-corrosion primer. An electrical current is applied, causing the primer to bond to the metal surface at a molecular level. Every nook, crevice, and corner is coated evenly, providing unmatched rust protection. The G-Class was originally built for military duty, and this durability-focused philosophy continues today. After the e-coating, the body is cured in an oven at temperatures around 180 degrees Celsius. The curing hardens the primer and sets the foundation for the paintwork that will follow. Then comes the application of the base coat, color layers, and clear coat, each sprayed meticulously in high-tech painting booths. The factory offers a broad range of colors, from conservative blacks and silvers to vibrant custom finishes from the G Manufacture Personalization Program. Incredibly, many G-Class vehicles receive their paint by hand spraying, not automated robots. This allows greater control and customization for two-tone finishes, matte effects, and hand-masked accents. The painted body then returns to another round of inspections. Factory workers use light tunnels and soft cloths to detect even the smallest specks of dust, paint sagging, or orange peel textures. If needed, technicians wet sand and polish the affected areas manually. This is one of the most time-consuming parts of the process, but it ensures that the G-Class leaves the paint shop with a flawless, mirror-like surface. With the body now painted and prepped, attention turns to the chassis, the rugged ladder frame that defines the G-Class's off-road DNA. Unlike unibody cars, where the structure and body are fused, the G-Class separates these two elements, a design that offers superior strength and modularity. The chassis is fabricated from thick-gauge steel and welded into a rectangular framework with multiple crossmembers and mounting points. It's engineered to endure extreme torsional loads from uneven terrain, rock crawling, and high-speed travel over unpaved surfaces. The entire chassis is then treated with a special powder coating that protects it from gravel, salt, moisture, and mechanical wear. At this point, the chassis begins its mechanical assembly. Giant overhead conveyors lifted into place on a moving assembly line. Suspension components are added first. The G-Class uses a double wishbone front suspension and a rigid rear axle with trailing arms and coil springs, all designed for articulation and ride comfort. Workers mount control arms, install air or coil springs depending on the configuration, and torque each fastener to precise specs using digital torque wrenches that record every application for quality traceability. Drive shafts, differentials, and the transfer case follow next. The G-Class features 3 locking differentials, front, center, and rear, making it one of the most capable factory off-roaders ever built. These components are pre-assembled in sublines and arrive at the main chassis line just in time for installation. Each differential is bench tested before being mounted, and once installed, hydraulic and electronic connections are secured and checked for sealing integrity. Next, the engine and transmission arrive. These powertrains are built separately, typically at Mercedes powertrain facilities, and delivered fully dressed with wiring harnesses, fuel systems, and control modules already in place. A robotic hoist lowers the engine and transmission into the chassis as technicians bolt it down to reinforced subframe mounts. The transmission tunnel is lined with heat shielding and the exhaust system is connected. Stainless steel manifolds, catalytic converters, and mufflers are all aligned with laser guidance systems to ensure proper clearance and vibration isolation. As the powertrain is secured, attention turns to the braking and steering systems. High-performance disc brakes with multi-piston calipers are installed on each wheel hub. Brake lines are routed with stainless steel fittings and then bled using automated vacuum machines to ensure a perfect seal and no air bubbles. The power steering rack is attached and aligned, and its fluid circuits are pre-flushed to remove any contaminants. At this stage, the chassis is essentially a rolling platform, ready to meet the painted body that has been traveling in parallel on a separate line. Continuing our journey into the heart of the Mercedes-Benz G-Class assembly process, we arrive at the moment of mechanical matrimony, a pivotal point known within the factory as the marriage. This step is one of the most anticipated stages in any automotive plant, but here in Graz, it carries almost ceremonial weight. The moment when the meticulously painted body is lowered onto the fully built ladder frame chassis transforms a collection of high-grade parts into what begins to truly resemble a finished G-Class. The process begins with both the body and the chassis arriving at the marriage station on two separate automated conveyor lines. Precision and timing are essential, as the chassis is lined up beneath the suspended body shell. A series of hydraulic lifts and alignment pins begin the delicate work of bringing the two together. Technicians verify multiple reference points using laser measurement tools to ensure the body mounts align perfectly with the corresponding points on the chassis. The process may appear straightforward, but in reality, the tolerances are extremely tight, within a single millimeter. Any deviation could lead to misaligned panels, noisy interiors, or handling inconsistencies. Once the alignment is verified, the body is carefully lowered using a multi-axis robotic gantry system. Specialized bushings are inserted between body and frame to absorb vibrations, and bolts are torqued down using synchronized electric torque tools. These tools not only apply the correct force, but also record each torque event digitally for traceability. In total, dozens of mounting points are secured during this stage, creating a permanent bond between body and chassis. With the vehicle now structurally complete, the next steps shift focus to the installation of electrical systems and interior components. The G-Class is known for its advanced technology, luxury appointments, and off-road capability, all of which require an intricate network of electronics. Wiring harnesses are delivered to the line pre-assembled and bundled according to specific vehicle configurations. Each harness includes connectors for power distribution, lighting, infotainment, sensors, airbags, and the drivetrain management system. Installation of these harnesses is done mostly by hand due to the complexity and variability of options in each vehicle. Workers snake thick bundles of cables through the body structure, routing them through the firewall, behind the dashboard frame, under the floor, and along the roof rails. Clamps and cable guides ensure the wiring remains secure and doesn't rattle or chafe over time. Diagnostic computers are connected at this stage to confirm continuity, check for shorts, and verify module communications over the vehicle's CAN bus network. While this is happening, the HVAC system is assembled and installed. This includes the heater core, evaporator unit, blower fans, and electronic control motors that adjust airflow and temperature zones. The G-Class features multi-zone climate control, so ducting is routed with exacting precision through the dash, footwells, and rear cabin areas. Once the climate system is in place, the dashboard sub-assembly is installed as a single module. This enormous component includes the infotainment screen, control buttons, ambient lighting strips, and the central air vents. Workers use vacuum suction lifts to guide the dash into place without damaging the painted surfaces or soft leather trim. Now comes one of the most craftsmanship-intensive stages in the entire production, the installation of the interior. Unlike many mass-produced vehicles that use synthetic fabrics and machine-mounted panels, the G-Class is fitted largely by hand, using real materials: leather, wood, aluminum, and piano black lacquered plastics. The seats are built separately and upholstered using hides that are individually inspected for imperfections. Skilled trimmers sew the leather together using double stitching patterns that match the exterior color or the customer's specification. Once finished, the seats are bolted into the vehicle with electronic seat module calibration to ensure proper memory function and lumbar support. Door panels follow next. These are assembled in parallel stations where components like speaker grills, switches, ambient lighting, and leather inserts are bonded together before being mounted. Each panel is carefully pressed into place and tested for fit, sound insulation, and tactile feedback. The sound of a G-Class door closing is legendary, an unmistakable mechanical clunk that speaks to solidity. Achieving this sound requires a precise interplay of hinges, rubber seals, door weight, and locking mechanism geometry. Carpeting, floor mats, headliners, and trim moldings are next. Workers stretch and press these components into place using heat guns and hand rollers to ensure wrinkle-free surfaces and tight fits. The sunroof assembly is dropped in from above and sealed with multi-layer gaskets to prevent leaks. All the while, every stage includes quality inspections using both visual checks and functional tests. Is the stitching even? Does the infotainment system respond instantly to input? Is the rear seat heating element warming to spec? These aren't afterthoughts. They're checked and verified at every step. With the interior mostly complete, attention now turns to the installation of exterior finishing components. This includes the lighting systems, trim pieces, bumpers, grills, and the wheels and tires. Headlights and taillights are delivered in sealed packaging and installed using torque-controlled tools to avoid over-tightening. Each lighting unit is powered on and subjected to an alignment procedure that ensures optimal beam projection. The G-Class often includes LED matrix lighting, so precise calibration is required to ensure adaptive lighting functions correctly on the road. The bumpers, both front and rear, are more than decorative. They contain impact absorbers, parking sensors, and, in some models, radar modules for adaptive cruise control. These systems must be aligned with the vehicle's central ECU and tested for accuracy. The grille, which houses the iconic Mercedes three-pointed star, is mounted next, followed by trim pieces such as side skirts, fender flares, and the protective body cladding that's especially important for off-road variants. Wheels and tires are mounted towards the end of this phase. Each tire is balanced individually before mounting to minimize road vibration. The G-Class uses either 18-inch or larger wheels, depending on the model, and all are fitted with performance, all-season, or off-road tires. Lug nuts are torqued in a star pattern and then double-checked by a second technician for safety. The signature rear-mounted spare wheel is added last, requiring special reinforcement brackets to support its considerable weight. At this point, the vehicle is externally and internally complete, but it hasn't yet proven itself ready for the road. That's where the end-of-line testing begins. First, each vehicle is rolled onto a chassis dynamometer for a systems check. This stationary rolling road allows technicians to simulate driving conditions without the vehicle leaving the factory. Engines are started and revved through a range of RPMs. The transmission is cycled through its gears. Braking systems are tested under controlled load. Onboard diagnostics scan every system for fault codes, and calibration values are adjusted in real time. Next, the G-Class is taken into the water testing booth, a sealed chamber where high-pressure water jets blast the vehicle from all angles. This simulates heavy rainfall and river fording to confirm that all seals and gaskets are intact. Doors, windows, the sunroof, and even antenna mounts are tested for ingress. Any leaks are flagged for immediate remediation. Following the water test, vehicles are subjected to a visual inspection tunnel with multi-angle lighting. Here, inspectors walk around each unit, examining body panel gaps, paint reflections, wheel alignment, and emblem placement. Mirrors are adjusted, wiper blades tested, and final protective films removed. Finally, the G-Class is driven onto a short test track either inside or just outside the factory. This final road test includes a variety of surfaces: cobblestones, incline ramps, sharp turns, and slalom sections. Trained drivers listen for abnormal noises, feel for steering alignment, and evaluate ride quality. Any deviation from spec sends the vehicle to a special adjustment area for corrections. Only once all tests are passed does the vehicle receive its final factory seal of approval. Even then, however, the process isn't over. Depending on the destination, additional country-specific requirements are installed. These may include compliance labels, GPS regional settings, localized safety equipment, and left or right-hand drive adjustments. Paperwork is finalized, including the build sheet, quality inspection records, and shipment documentation. The vehicle is then either driven onto a covered transport truck or loaded into a sealed container for overseas shipping. Now that the G-Class has completed its rigorous in-factory berth, a process involving welding, painting, assembly, and exhaustive quality checks, it embarks on the next critical phase of its journey: preparation for global distribution. This phase, though less visually dramatic than robotic welders or precision-aligned dashboards, is nonetheless a feat of coordination and logistics. The moment a G-Class rolls out of the Magna Steyr facility in Graz, Austria, it transitions from handcrafted engineering marvel to a globally positioned product, bound for showrooms, private collections, mountain trails, or inner-city avenues. But before it reaches any of these, there is still a tremendous amount of effort that goes into protecting, staging, and transporting each unit with the same care and attention to detail used in its creation. Once a G-Class vehicle has passed its final road test and received its full quality release documentation, it is driven under its own power to the staging area adjacent to the main plant. Here, specially trained logistics personnel begin the final detailing and protection process. Although the vehicle is fully finished, there is a layer of preparation necessary to ensure it survives the rigors of global shipping. Protective films are applied to sensitive areas: the hood, roof, door sills, mirrors, and corners of the bumpers are covered with temporary plastic guards that resist scratches, UV exposure, and road grime. The alloy wheels are often wrapped in foam liners or protective rings to prevent damage from transport straps or accidental impacts during loading. Interior surfaces are also shielded with plastic covers over the seats, infotainment screens, and floor mats. Every vehicle is now tagged with a unique, VIN-linked logistics barcode, which details its destination, shipping method, port of entry, and delivery window. This data is integrated with Mercedes-Benz's global tracking system, allowing every stakeholder, from plant logistics to overseas dealerships, to monitor the car's location in real time. Depending on its final destination, the G-Class may undergo additional region-specific programming. For example, a vehicle bound for North America will be loaded with US-specific emissions calibrations and compliance documentation, while one heading to the Middle East might receive enhanced climate control settings and reinforced dust filtration for desert conditions. Next, the vehicle is routed to one of several outbound transport modes. For European customers or regional delivery, G-Classes are typically driven onto covered car haulers, large multi-deck trucks designed to transport 6 to 8 vehicles at a time. These trucks have air ride suspensions to reduce vibrations and protect the delicate ride height sensors and chassis calibration. For vehicles headed abroad, the process is more elaborate. The G-classes are driven into rail cars or loaded into intermodal shipping containers, which are then routed to seaports like Bremerhaven in Germany or Koper in Slovenia. At the port, each container or open deck vessel is handled with specialized cranes and ramps that minimize jostling. It is worth noting that many G-Class models, particularly Special Edition or G Manufacture builds, are transported in sealed containers to prevent salt spray, sun fading, or theft. The voyage by sea can take several weeks. For example, vehicles headed to North America might pass through the English Channel, cross the Atlantic, and dock at ports like Baltimore or Brunswick. Once at port, they are processed through customs, emissions, and safety verification, all under the oversight of Mercedes-Benz regional distribution centers. Then comes a second round of quality control, sometimes called a PDI or pre-delivery inspection. This includes checking tire pressure, recalibrating navigation systems to the local GPS constellation, adjusting language and date formats, and inspecting the vehicle for any damage incurred during shipping. If a vehicle has traveled thousands of kilometers by rail, truck, and sea, this inspection is crucial to maintain the brand's reputation for perfection. Once cleared, the G-Class is dispatched to its final destination, a dealership, fleet customer, private buyer, or regional collection center. Even here, the aura of exclusivity surrounding the G-Class continues. Many buyers opt for specialized white glove delivery, wherein the vehicle is transported by single car covered trailer and presented with ceremonial fanfare, unveiling cloth, branded key boxes, and sometimes a personal orientation session with a brand specialist. The delivery experience is designed to match the vehicle's pedigree, but beyond the logistics and visual pageantry, what truly makes the G-Class remarkable is that even after all of this effort, the vehicle is still, at heart, a rugged, off-road tool. Every single G-Class, whether destined for a downtown penthouse or a mining operation in Siberia, is built to the same foundational spec: full-time four-wheel drive, locking differentials, a 2-speed transfer case, and a ladder frame that could survive military deployment. That's the irony and the charm of the G-Class. It's capable of climbing a 45-degree incline, fording rivers, and navigating icy switchbacks, yet it will just as often be used to roll quietly over cobblestones in Monaco or park beneath luxury boutiques in Dubai. The factory doesn't know what fate awaits each G-Class, and it doesn't matter. Each one is engineered for extremes, regardless of how pampered its life may be. Now, let's take a moment to consider the people behind this machine. While many modern automotive factories are fully robotic and optimized for scale, the G-Class production line retains an unusually high proportion of human labor. Over 1,500 skilled workers at Magna Steyr contribute to its assembly, many of them having decades of experience with the model. Their knowledge, much of it gained through repetition, mentoring, and attention to the tactile feedback of materials, is irreplaceable. They know the right torque by feel. They can spot a millimeter-wide gap from across the room. In a time where artificial intelligence and robotics are reshaping the manufacturing landscape, the G-Class stands as an example of how artisanal skills still hold tremendous value. This blend of traditional craftsmanship and modern precision engineering is particularly evident in the G Manufacture program. Here, customers can personalize nearly every aspect of their G-Class, from more than 30 exterior paint killers to a wide range of leather hues, stitching patterns, interior trims, and wheel designs. If a buyer wants orange leather with green piping and a matte olive exterior, they can have it. These builds are not separated into another facility. They're integrated into the main production line with designated bays where craftsmen apply these one-off features by hand. This level of customization presents huge logistical challenges, matching materials to build slots, keeping non-standard parts in stock, and maintaining quality across thousands of permutations. Yet the factory has embraced this complexity as a way to deepen the bond between owner and vehicle. Meanwhile, let's not forget the rigorous quality control that continues to influence every element of the G-Class's construction. For example, every powertrain used in the G-Class, whether the twin turbocharged V8 in the AMG variant or the inline-6 in the standard model, undergoes cold testing prior to installation. In cold testing, engines are spun up using electric motors without firing them, while sensors measure oil pressure, bearing resistance, valve timing, and sealing. This ensures that only powertrains meeting exact tolerances make it to the assembly floor. Similarly, each differential assembly is bench tested for noise and balance before integration into the vehicle. It's not enough for components to fit. They must perform to exacting standards. Even paint color undergoes scientific scrutiny. After application, each painted body is checked using spectrophotometers, special instruments that detect even the slightest variation in hue, brightness, and saturation. This is especially important when replacing panels after damage or repair. Consistency in color across different batches of paint and lighting conditions is notoriously difficult. Yet, Mercedes insists on millimetric perfection, even for colors that might only be chosen by 1 in 1,000 customers. It's this obsessive attention to detail that makes the G-Class stand out, and it's why its production process is stretched over more than 100 hours per vehicle. Where other vehicles are designed for efficiency, the G-Class is designed for excellence. Every step, from welding to upholstery, from software calibration to final wheel alignment, is geared toward creating something more than just a car. It's a statement of what happens when engineering, tradition, and passion come together under one roof. Before any assembly begins on the factory floor, months of design and configuration have already taken place through digital modeling and client collaboration. Scania offers thousands of configurations, from cab types and engine sizes to axle arrangements and emissions profiles. Every order is configured down to the most minute specification using proprietary software systems that feed directly into the production planning systems of the factory. This digital integration ensures that each vehicle is built precisely to customer requirements, and it sets the stage for the just-in-time production model that Scania factories are known for. The process truly begins at the component level, starting with the chassis frame, the very skeleton of the truck. These frames are not formed on-site at every assembly plant. Rather, they are usually manufactured at specialized Scania facilities, such as the one in Oskarshamn, Sweden, which is renowned for its advanced laser welding and robotic bending capabilities. The raw material used is high-strength structural steel, delivered in coiled sheets or cut plates from steel mills. These sheets undergo multiple forming processes, including automated press bending, where robotic arms position the steel under immense pressure to form the longitudinal beams that serve as the base of the truck frame. After initial shaping, the steel beams enter a sophisticated robotic welding line. Here, computer-controlled robotic arms move with choreographed precision to apply dozens of welds to each frame component. Each welding head is equipped with sensors that monitor temperature, pressure, and seam alignment in real time. This ensures not only the structural integrity of the frame, but also guarantees a level of repeatability and strength that simply cannot be matched by manual welding. After welding, the frames undergo surface cleaning using shot blasting, a process that fires small steel pellets at high velocity to remove mill scale and other surface impurities, leaving behind a clean, textured finish ideal for powder coating. Next comes the anti-corrosion treatment, which is absolutely vital given the operating environments that Scania trucks face globally. The prepared frame is dipped into large immersion tanks containing anti-corrosive coatings. These coatings bond to the steel surface and offer long-term protection against rust and environmental wear. Once coated, the frame is cured in high-temperature ovens to ensure the treatment hardens properly and maintains adhesion through the vehicle's life cycle. While chassis frames are being processed, the cab structure, the cockpit of the truck, is being built in parallel. Scania's cab production is typically handled in highly automated body shops. The core of the cab begins as pressed Cersei steel panels that are stamped into shape using massive hydraulic presses. Each press can apply hundreds of tons of force, transforming flat sheet metal into complex structural elements like roof panels, side walls, and floor pans. These pressed panels are then moved by robotic arms into positioning jigs where they are tack welded together to form the basic cab shell. The welding of the cab shell is another highly automated process. Industrial robotic arms, fitted with multiple welding torches, navigate around the jig to apply hundreds of spot welds with exacting precision. Sensors track the positioning down to millimeter level tolerances, ensuring every cab structure is perfectly square and secure. As with the chassis frame, once the cab shell is fully welded, it is subjected to shot blasting and anti-corrosion dipping. After treatment, the cab shell is baked in industrial curing ovens and then passed into the next phase, painting. The painting process is one of the most visually striking steps in the factory. Trucks are typically painted in customer-specific colors, and Scania's paint shops are designed to switch colors rapidly with minimal waste. First, the cab shell enters a cleaning station, where it is rinsed, degreased, and coated with a phosphate layer to promote paint adhesion. Next, it enters the electrocoating tank, a large bath filled with a water-based paint solution that is electrically charged. The cab is submerged and an electrical current is applied, causing paint particles to bond electrochemically to the metal surface in a uniform layer. This electrocoat layer is corrosion resistant and acts as a primer for the top coat. Once cured in an oven, the cab shell enters the color booth. This area is a climate-controlled environment where automated paint robots, guided by 3D scanning systems, apply base coat and clear coat layers with astonishing accuracy. The robotic arms mimic human wrist movements, but with far more consistency and speed. Depending on the finish, additional layers like metallic flakes or special high-gloss coatings may be added. After painting, the cab passes through a final curing oven, where the coating is hardened under controlled heat conditions. While the cab and chassis are progressing through their respective lines, work begins on the engine, the heart of every Scania truck. Scania is known globally for manufacturing its own engines, and the engine assembly takes place in facilities with a near-surgical level of cleanliness. Engine blocks arrive from foundries where molten iron has been cast into precisely machined forms. These blocks are cleaned, inspected, and then sent through CNC machining lines to be drilled, bored, and honed. Critical components like cylinder bores, oil channels, and mounting faces are machined to micrometer level tolerances to ensure proper sealing and performance. The engine assembly line is a hybrid of human craftsmanship and automated precision. Components like the crankshaft, camshaft, pistons, and connecting rods are assembled using semi-automated workstations where torque-controlled tools tighten bolts to exact specifications recorded in a central database. Scania engines are known for their modularity. Many of the components can be shared across different engine variants, simplifying logistics and repair. Each engine is assembled in stages, with sensors and barcode tracking, ensuring that every step is validated before moving to the next station. Once the engine is fully assembled, it moves to the hot test cells, where it is connected to a computerized test rig and run under simulated load conditions. These test cycles verify oil pressure, emissions output, power delivery, and temperature control. The engine must pass every parameter before it is certified for installation. Failures are extremely rare due to the high degree of automation and quality control earlier in the process. By this stage in the production process, the frame, cab, and engine are all nearly complete. The next phase is the main assembly line, a linear path where all major components are brought together. This line stretches hundreds of meters through the heart of the factory and is divided into dozens of stations, each with a specific responsibility. Trucks move along the line on large powered platforms or guided vehicles, allowing workers and robots to access all sides without repositioning. The first step on the assembly line is the chassis outfitting, where the bare steel frame receives mounting brackets, fuel tanks, air tanks, electrical conduits, and brake lines. Each part is pre-assembled into kits that arrive from sub-assembly areas and are bolted on using torque-controlled tools. Workers scan every part's barcode into the digital tracking system, ensuring complete traceability from installation to delivery. As the chassis assembly progresses down the main line, the stage is set for one of the most critical moments in the truck's birth: the installation of the drivetrain. This includes the mounting of the engine, transmission, clutch assembly, and propeller shafts, all aligned and fitted with micrometer precision. The engine, having already passed its hot test, arrives at the drivetrain installation zone pre-mounted on a subframe cradle. This subframe allows the engine to be maneuvered easily and with extreme accuracy. Overhead, automated hoists fitted with dynamic positioning systems gently lower the engine into the frame rails. A laser-guided alignment system ensures that the engine mountings perfectly match the pre-fitted brackets on the chassis. At this point, technicians, supported by robotic arms that hold the engine weight, secure the mounting bolts using calibrated torque wrenches. Every bolt torque is recorded and logged digitally to create a traceable quality certificate tied to the vehicle's serial number. Following engine installation, the gearbox, a heavy and complex component, is hoisted into position behind the engine. Scania often uses its own automated manual transmissions, which integrate seamlessly with the engine via a robust clutch assembly. The clutch mechanism is pre-aligned with the flywheel, and the entire transmission unit slides onto guide pins with barely a millimeter of clearance. Here, technicians connect the hydraulic lines, gear linkages, and electrical connectors that allow for automated gear shifting, engine brake interaction, and adaptive cruise functionality. With the drivetrain in place, attention turns to the rear axle and suspension systems. Depending on the truck's intended use, long-haul, construction, or specialized applications, different axle configurations are applied. Some trucks feature a single rear axle, while others utilize tandem configurations or even additional tag axles. The axles arrive pre-assembled from Scania's axle plant, complete with brakes, hubs, and suspension linkages. They are lifted into place by hydraulic jacks and bolted to the chassis with spring packs, air bellows, or hydraulic suspension systems already integrated. Next comes propeller shaft installation, connecting the transmission to the rear axles. These shafts are balanced dynamically at the supplier's facility to prevent vibration. Universal joints are fitted with greased couplings and protective covers, ensuring long-term durability under high torque loads. At this point, the foundation of the truck's powertrain is complete. However, without electrical and pneumatic systems, the vehicle would remain lifeless. The next station handles electrical harnessing and air system integration. Scania trucks feature an extensive network of electrical harnesses, connecting everything from the engine control module and dashboard to rear light clusters and sensors. These harnesses are laid out in custom configured looms that match the specific vehicle configuration. Workers unroll and clip these looms into pre-installed brackets along the chassis rails, securing them with fasteners and protective sheathing. The plugs and connectors are then checked for correct mating, and a low voltage continuity test is performed to validate the integrity of each circuit. In parallel, technicians install air hoses and pneumatic control lines, crucial for the operation of brakes, suspension, and gear shifting systems. Scania uses color-coded hoses for easy identification: blue for service brakes, red for emergency lines, yellow for auxiliary systems. The hoses are pressure tested before installation and connected to manifold blocks fitted with quick-release couplings. Once in place, the entire pneumatic system is subjected to a leak-down test using compressed air. Pressure sensors monitor the rate of decay, and if it exceeds a predefined threshold, technicians isolate and rectify the issue before the vehicle proceeds. With the chassis now wired, plumbed, and powered, the moment arrives for the cab to be mounted. The painted and primed cab shell, now fully treated and cured, has been proceeding through a parallel line where interior components are added. Before it is even lifted onto the chassis, the cab undergoes pre-fitting of the dashboard, insulation, wiring, and climate control systems. The dashboard arrives as a single pre-wired module complete with instrument cluster, infotainment unit, control switches, and HVAC ducting. It is installed into the cab using a robotic arm that slides the assembly into its predefined slots and secures it with vibration-resistant fasteners. At this stage, seats, pedal boxes, steering columns, and interior trim pieces are installed by skilled technicians. Each element is configured based on customer preferences, from seat fabric and placement to storage compartments and auxiliary switches. Once the interior is complete, the cab is transported via an overhead conveyor to the cab marriage station, a precise and dramatic point in the assembly process. Here, a massive cab lifting robot equipped with multi-axis movement positions the cab above the chassis. Using laser alignment sensors and pre-programmed coordinates, the system lowers the cab onto 4 chassis mounting points. Pneumatic mounts or mechanical bushings are inserted to dampen vibrations and provide ride comfort. Once seated, high-strength bolts are applied with synchronized torque tools, and the cab becomes one with the chassis. Following this, technicians connect the main wiring harness and pneumatic lines from the cab to the chassis, a process known as cab chassis interface. These connections include CAN bus data lines, power feeds, brake system controls, and auxiliary switches. As soon as these connections are complete, the vehicle is able to wake up electronically for the first time. A diagnostic tablet is plugged into the OBD port, and the truck performs a systems check. Any discrepancies or error codes are logged and addressed before the truck moves forward. The vehicle now advances to the fluid filling and commissioning station. Here, all essential fluids are added, including engine oil, coolant, transmission fluid, brake fluid, power steering fluid, AdBlue, and diesel fuel. Each fluid fill station uses metered pumps that log exact fill quantities and pressure levels. Automated sensors inside the engine and tank systems confirm that fluid levels are within range before proceeding. Once filled, the truck moves to the initial startup station, where the ignition is switched on for the first time on the line. The starter motor cranks the engine, which should come to life smoothly. A team of technicians monitors engine performance, checking for warning lights, irregular noise, or leaks. The air compressor charges the brake system, and all pneumatic circuits are tested for function. This includes pressing the brake pedal, triggering the parking brake, and cycling the air suspension. Next, the truck undergoes a dynamic rolling road test inside a fully enclosed test chamber. The vehicle is driven on rollers that simulate real-world road resistance, while various systems are tested under load. This includes acceleration tests, ABS brake tests, gear shifting patterns, cruise control behavior, emission system feedback, and traction control activation. The data is streamed in real time to diagnostic software, where engineers verify that the truck operates within all calibrated parameters. Upon passing the rolling test, the truck is driven into the final inspection bay. Here, inspectors conduct a detailed walk-around, checking for cosmetic imperfections, paint defects, missing trim pieces, or loose fittings. Each headlight, indicator, fog lamp, and brake light is checked for functionality and alignment. Mirrors are adjusted, windscreen wipers tested, and all cabin electronics, including navigation, air conditioning, radio, and USB ports are verified for operation. Once the final inspection is complete, the vehicle moves to the finishing line, where customer-specific decals, model badges, and optional accessories like bull bars, sun visors, or additional lighting rigs are added. Every Scania truck is tailored to its owner's vision, and this station gives each one its unique identity before it leaves the factory. The completed truck now rolls into the validation and delivery area, where all data from the manufacturing process, component serial numbers, torque values, diagnostic results, and inspection records are compiled into a digital certificate of compliance. This certificate accompanies the truck throughout its life, acting as a birth record for servicing and warranty purposes. At this point, the truck is technically complete, but its journey is far from over. In the next section, we will follow how Scania handles post-factory logistics, transport, dealer preparation, and delivery to the end customer, along with insights into technological innovations and modular production strategies that continue to shape Scania's dominance in global trucking. Once the truck passes its final on-site validation and is cleared for delivery, it enters a new phase in its life cycle: post-factory logistics and outbound handling. This transition is just as carefully orchestrated as the build itself. A Scania truck may be fully assembled, tested, and polished, but before it can reach the customer, it must navigate a labyrinth of post-production processes, including staging, transport planning, documentation handling, and final handover preparation. This stage marks the convergence of manufacturing precision and supply chain excellence. The first step in this process is vehicle staging, which occurs in a designated outbound yard adjacent to the factory. This outdoor staging area is organized with military-grade precision, divided into zones based on delivery destination, vehicle type, and shipping method. Trucks are driven, not towed, from the final inspection area to the appropriate staging bay. Each vehicle is equipped with temporary wheel covers and protective wraps over vulnerable surfaces like mirrors, windshields, and chrome trim. These protective measures prevent damage during transport, especially when trucks are carried on open trailers or cargo vessels. In the outbound yard, every truck is again scanned using RFID and barcode systems, confirming its identity and correlating it with a live logistics management system. This software tracks all trucks awaiting dispatch and organizes them according to optimal shipping schedules. Depending on the final destination, a truck may be routed for domestic road delivery, loaded onto a rail car, or prepared for maritime shipment if it's headed overseas. Each route comes with its own handling protocols. For domestic deliveries within Europe, trucks are often driven under their own power by certified logistics drivers. These drivers, trained in Scania vehicle systems, are responsible not only for transportation, but for monitoring the vehicle en route. Before leaving, they perform a second-round walk-around inspection, checking fluid levels, tire pressures, and verifying that the truck matches its shipping manifest. Each journey is GPS tracked and time logged, ensuring total visibility for the customer and Scania's distribution center. If the truck is destined for international export, the logistics become more complex. Vehicles headed for distant markets like South America, Asia, or Africa are transported in batches, often using ro-ro vessels, or roll-on/roll-off ships. Prior to shipment, trucks undergo a pre-export treatment. This includes draining fuel to a minimum safe level, checking emission systems to meet port regulations, and applying additional weatherproofing layers to vulnerable components. If local regulations require specific emissions calibrations or market-specific software updates, these are applied at this stage by an outbound technician using a portable diagnostics tablet. Trucks bound for shipping are driven onto specialized transporters and secured with heavy-duty wheel chocks and tie-down systems. These transporters then carry them to port terminals, where logistics partners manage loading onto ro-ro decks using low-speed maneuvers to protect drivetrains. Throughout this entire handover process, every movement is tracked, and a digital chain of custody is maintained. In some cases, vehicles are not shipped fully assembled. For certain regions with import restrictions or high shipping costs, Scania employs a CKD strategy, complete knockdown. In this method, trucks are partially disassembled after factory completion and packed into containers, then shipped to regional assembly centers. Here, local teams reassemble the trucks under supervision, with full adherence to Scania's engineering and quality standards. This allows Scania to maintain a global footprint without needing a full manufacturing line in every country. Back in Europe, however, trucks that remain in their final configuration are delivered either to regional logistics hubs or directly to dealerships, depending on customer contracts. These logistics hubs serve as a final buffering point before customer delivery. Here, each truck is cleaned again, checked for any transport damage, and in some cases, fitted with market-specific accessories like tachographs, radio equipment, or fleet telematics systems. These are often added just before delivery to ensure compliance with local transport laws or client specifications. Once the vehicle reaches a Scania dealership or customer depot, a final pre-delivery inspection, or PDI, is conducted. This check is performed by certified dealer technicians who cross-reference the vehicle's production history with a detailed checklist covering all operational systems. This includes cabin electronics, tire and wheel torque, headlight alignment, climate control operation, door seals and warning systems. Any required updates to onboard software, such as navigation databases or telematics modules, are downloaded and installed. At this point, the truck is nearly ready for handover to the customer, but Scania doesn't simply hand over the keys. For fleet clients or first-time buyers, a dedicated Scania delivery specialist may conduct a full walkthrough of the truck's systems. This includes explaining the adaptive cruise control functions, emergency braking systems, lane departure warnings, engine braking modes, and fuel-saving strategies. Drivers are often given a demonstration of how to use Scania's onboard telematics system, known as Scania Fleet Management, which allows fleet operators to monitor fuel consumption, driver behavior, vehicle health, and maintenance schedules in real time. This entire process, from component welding to client delivery, is only possible due to the extraordinary level of digital integration within Scania's production and logistics ecosystem. Every part, process, and movement is connected through a unified IT platform that synchronizes planning, inventory, production, and outbound delivery. This digital backbone allows Scania to offer mass customization at industrial scale, which is rare in heavy vehicle manufacturing. Beyond the sheer logistics of delivery, what truly sets Scania apart is its modular architecture, a production strategy that deserves closer inspection. Unlike many truck manufacturers that rely on rigid product lines and bespoke configurations that increase complexity, Scania uses a tightly controlled system of shared components and scalable designs. For instance, the same type of engine block can be used across multiple power ratings, with changes in turbocharging, fuel injection mapping, or transmission pairing creating different performance profiles. Cab shells also share mounting points, crash structures, and roof lines, with final variations created through bolt-on panels, interiors, and accessories. This modularity dramatically reduces the number of unique parts required on the factory floor, streamlining logistics and reducing time between customer order and vehicle build. It also ensures that spare parts are widely compatible, simplifying aftermarket servicing and reducing downtime for fleet operators. For Scania, modularity is not just a design choice. It is a strategic manufacturing philosophy that underpins everything from tooling and robotics to workforce training and dealer support. Inside the factories, this approach enables a high degree of automation. Robotic systems handle repetitive, precision-critical tasks such as welding, painting, and component fastening. Yet the human role remains central, especially in final assembly, inspection, and troubleshooting. Scania invests heavily in worker training, with programs that teach technicians how to read digital work instructions, use torque validation tools, and interpret real-time diagnostics data from vehicles in production. These skills are critical in maintaining quality across a product range that offers nearly infinite customization. To further enhance efficiency and quality, Scania has implemented smart factory technologies, including IoT sensors embedded throughout the production line. These sensors monitor equipment status, production flow, and product quality in real time. If a robotic welding arm shows signs of drift, or if a torque gun applies a value slightly out of spec, the system alerts supervisors instantly. Predictive maintenance algorithms analyze these data streams to prevent unplanned downtime, allowing equipment to be serviced before failure occurs. Sustainability is another cornerstone of Scania's manufacturing model. The company has made major investments in reducing the environmental impact of its facilities. This includes using renewable electricity, water recycling systems in paint shops, and closed-loop material recovery processes. For instance, steel offcuts from cab panel stamping are collected, sorted, and returned to suppliers for reprocessing. Paint overspray is captured and filtered before it reaches the atmosphere, while heat generated by curing ovens is recycled to warm nearby buildings. Even the logistics fleet used to move trucks from plant to port has undergone greening. Many Scania factories use their own battery electric or gas-powered truck transporters for short-range movements, reducing emissions around the factory campus. Scania's long-term goal is to create a fossil-free value chain, meaning not just fossil-free trucks, but a zero-emissions process behind every vehicle's creation. What emerges from all of this is not just a truck, but a precision-built, software-integrated, environmentally conscious transport machine designed to serve its owner with maximum uptime and minimum operating cost. Every bolt torqued, every panel painted, and every test completed is done with the understanding that this machine will soon be barreling down highways, climbing mountains, or navigating mines, often in the most demanding environments on Earth. And so, as a freshly built Scania truck pulls out of the outbound lot under its own power, fully tested, aligned, and gleaming in its custom livery, it carries with it not just cargo, but a legacy of Scandinavian engineering, lean production mastery, and digital age innovation. As the newly minted Scania truck rolls off the assembly line and onto the road, its journey as a manufactured product may be complete, but its role as a data-rich, high-performance logistics tool is just beginning. What differentiates Scania in the world of heavy-duty vehicles is not just its robust physical engineering, but also the intelligent integration of software and digital systems embedded throughout the truck. These features are not just bolted on at the end of production. They are enabled and supported throughout every stage of the manufacturing process. At the heart of this smart infrastructure is the Scania Communicator, a telematics control unit installed during the cab outfitting phase. This device connects the truck to Scania's fleet management system and remote diagnostics platforms. It functions as a two-way communications gateway between the vehicle and Scania's global network, transmitting real-time data on vehicle health, driver behavior, location, and fuel consumption. While the physical hardware is relatively compact, its installation is incredibly precise. During assembly, technicians route antennae, signal cables, and CAN bus interfaces through pre-designed channels in the cab, ensuring electromagnetic compatibility and resistance to vibration. The communicator's integration enables predictive maintenance, a significant evolution in vehicle lifecycle management. Throughout operation, the truck continuously monitors dozens of performance parameters: oil pressure, coolant temperature, brake wear, turbocharger pressure, emission levels, and more. These data points are compared against factory thresholds, and if any system approaches a condition that could cause failure, an alert is generated. This could trigger anything from a simple driver notification to a pre-scheduled service appointment at the nearest Scania workshop. It is a direct result of a factory design philosophy where the vehicle's digital nervous system is assembled and validated just as rigorously as its mechanical one. Alongside predictive maintenance, the truck's electronic control systems, also installed and configured on the assembly line, provide a high level of operational automation. Modern Scania trucks are built with dozens of ECUs, each responsible for a specific subsystem such as engine management, brake control, transmission logic, and climate systems. These units are connected via a redundant CAN network architecture, which not only increases fault tolerance, but also simplifies diagnostic procedures. During production, technicians use factory-grade diagnostic terminals to flash the appropriate firmware to each ECU, calibrate its behavior based on the truck's configuration, and verify communication across the entire electronic network. Scania's modular philosophy also extends to advanced driver assistance systems, many of which are pre-installed on the production line but activated or configured according to the customer's specifications. For example, the radar sensors used for adaptive cruise control and autonomous emergency braking are mounted on the front bumper during final assembly, precisely aligned to maintain millimeter-level accuracy over the vehicle's life. Similarly, the forward-facing camera that enables lane-keeping assistance is fitted behind the windshield during cab assembly, carefully positioned with a jig to ensure a clear, centered field of vision. Once installed, these components are connected to a centralized ADAS controller, which interprets sensor input and makes real-time driving decisions. These systems are subjected to a suite of calibration and alignment procedures before the truck leaves the factory. On the test track, radar and camera systems are validated against standard reference objects and road markers. In a controlled environment, the truck is driven through a calibration tunnel equipped with reflective targets, road signs, and lane markings designed to simulate real-world conditions. The vehicle's onboard systems must correctly interpret these stimuli, and if any discrepancies are found, technicians adjust sensor positioning or recalibrate software parameters using diagnostic interfaces. The cab interior too reflects a fusion of mechanical craftsmanship and digital design. Every detail, from the curvature of the dashboard to the responsiveness of touchscreens, is a result of ergonomic research and industrial design thinking. Scania recognizes that its drivers may spend days or even weeks living inside their cabs, and thus the manufacturing process treats the interior not just as a workplace, but as a living space. During cab outfitting, highly trained technicians assemble a range of custom options, from sleeper bunks and refrigerators to infotainment systems and integrated GPS navigation units. These elements are delivered to the line in kit form, each kit tailored to the customer's build sheet. Each cab interior is assembled under tightly controlled conditions to minimize dust, moisture, and static electricity, which could interfere with sensitive electronics. Seats are bolted to reinforced mounting points welded into the cab shell during body assembly, and each one is torque checked and height adjusted based on ergonomic templates. Touchscreen interfaces and instrument clusters are plugged into the vehicle's central network and tested via digital loopback to ensure correct display and input functionality. The HVAC system, including its filters, ducting, and thermoelectric units, is pressure tested and leak checked using nitrogen injection methods before being approved for operation. Another layer of sophistication is found in Scania's drive mode management system, also programmed during the production process. Depending on the truck's intended use, long-haul highway driving, urban logistics, construction haulage, or extreme terrain operation, the engine and transmission control units are calibrated to optimize for performance, fuel economy, or torque delivery. These calibrations are not simple throttle mappings. They include dynamic interaction between acceleration profiles, shift timing, exhaust gas recirculation rates, and even cooling fan activation thresholds. Engineers use proprietary software tools during assembly to upload the correct strategy maps into each ECU and then perform a synchronization cycle, ensuring all systems operate under a unified logic framework. In high-performance applications, such as off-road or heavy-load logistics, the truck may also be equipped with retarders, differential locks, and terrain modes. These features are controlled by modules installed under the dashboard and linked to the vehicle's main control network. Their installation involves not just physical mounting, but precise firmware configuration and sensor calibration. For instance, the differential lock actuator includes a position sensor that must be zeroed against the axle's true neutral position during installation. Once installed, these systems are tested during the dynamic run phase to ensure they engage and disengage correctly under simulated load. Meanwhile, aerodynamic elements such as roof deflectors, side skirts, and underbody fairings are installed toward the end of the main assembly line. These parts are often lightweight composite materials and are affixed using vibration-dampened fasteners and adhesive compounds designed to withstand high-speed airflow and temperature fluctuations. Their role in fuel economy is non-trivial. Even minor misalignments can increase drag, so final inspection stations are equipped with laser-guided measuring tools to verify exact positioning. Assembly teams cross-check these with 3D digital overlays displayed on large screens at the workstation. Beyond the truck itself, the factory also assembles and configures support technologies such as Scania Zone and Scania Driver Support. These tools are software-based but rely on correctly installed hardware during production. GPS modules, accelerometers, and vehicle-to-infrastructure communication units. Once activated, these systems allow operators to set geofenced zones where speed, emissions output, or engine performance is automatically regulated based on environmental or regulatory constraints. All of this logic is programmed through cloud-based platforms, but it depends entirely on the integrity of the installation work completed on the factory floor. Scania's embrace of digitalization also includes its end-of-line analytic systems, which collect every data point recorded during the truck's production. These include sensor calibrations, fluid fill quantities, software versions, torque readings, and test drive results. Once the truck completes its final quality checks, all this information is compiled into a digital build certificate, stored in Scania's central server network. This certificate not only proves the vehicle's compliance with legal standards, but it also becomes the backbone for future updates, diagnostics, and warranty assessments. Because of this meticulous build documentation, over-the-air updates can be rolled out to Scania trucks even after they have left the factory. The communicator module facilitates this functionality, allowing engineers to deploy firmware improvements, bug fixes, or performance upgrades without requiring the truck to return to a service point. This capability, made possible only because the production process embeds software management from the beginning, is rapidly becoming a key differentiator in the world of commercial transport. Perhaps most impressively, all of this technological complexity is achieved without sacrificing modularity, durability, or long-term serviceability. That's because every element, from wiring looms and ECUs to cab panels and control switches, is installed with future maintenance in mind. Harnesses are routed through accessible channels, ECUs are mounted in service boxes, and diagnostic ports are placed in standardized locations regardless of configuration. This consistency allows Scania dealers worldwide to service a wide variety of truck models with a common toolset and shared training, reducing cost and maximizing uptime for operators. The sum of all these innovations, from embedded sensors and adaptive software to modular electronics and digital infrastructure, is a Scania truck that operates not merely as a mechanical platform, but as a living, communicating system capable of learning, adapting, and reporting throughout its operational life. This vision of the modern truck as a responsive and evolving tool is deeply rooted in the manufacturing philosophy that builds it. A philosophy where every bolt, sensor, and wire is installed with purpose, tested with rigor, and documented with precision. Behind every meticulously crafted Scania truck lies a vast, highly organized human and mechanical ecosystem, an integrated workforce structure combined with world-class lean production methodologies. These systems are designed not only to uphold the brand's legendary quality standards, but to continuously improve them, model after model, day after day. While the end product might be steel, rubber, glass, and code, the beating heart of Scania's manufacturing process is its people and the smart systems they use. Scania's factory workforce is divided into several highly specialized roles, each optimized for a specific part of the assembly line or manufacturing process. These include welders, material handlers, electronic assembly technicians, test engineers, paint technicians, quality controllers, and logistics coordinators, among others. However, what truly distinguishes the Scania workforce is not rigid job segregation, but a dynamic cross-functional approach. Many workers are trained across multiple disciplines and encouraged to rotate tasks, which fosters a deeper understanding of the entire truck building process and enables agile response when production demands shift. This flexibility is essential because Scania operates under a pool-based production system, a fundamental component of its lean manufacturing strategy. Rather than producing trucks in large batches based on forecasted demand, Scania builds each truck to order, with every unit reflecting a unique customer configuration. When a client places an order, that request propagates through Scania's production planning system, triggering a cascade of component manufacturing, subassembly preparation, and final assembly scheduling. Every workstation on the line is updated with this incoming configuration data in real time, enabling the workforce to prepare for exact variations even before the chassis reaches their station. To manage this complexity, Scania employs a cell-based manufacturing layout, particularly in cab and engine subassembly. In this model, small autonomous teams, called production cells, take full ownership of assembling specific components or systems. Each cell is responsible not just for assembly, but also for quality control, minor maintenance of their equipment, and implementing continuous improvement initiatives. Workers within these cells hold daily stand-up meetings to review performance metrics, quality issues, and improvement suggestions. These meetings are an embodiment of Scania's commitment to Kaizen, or continuous incremental improvement. This improvement philosophy is not left to chance. Scania empowers its workers with structured frameworks like the Scania Production System, a variant of the famed Toyota Production System, adapted for the unique challenges of modular truck manufacturing. SPS is built around key principles like right from me, demand-driven flow, and standardized work with flexibility. Each station has visual boards displaying production targets, current throughput, quality alerts, and safety metrics. Any worker, at any time, can pull an andon cord, a signaling mechanism that immediately halts production to address a problem or anomaly. Far from being penalized, such actions are encouraged, reinforcing a culture of quality ownership. SPS also ensures that work instructions are standardized and digitized. At every station, touchscreens provide step-by-step guidance for each unique truck configuration, including diagrams, torque settings, part numbers, and even short instructional videos. This system ensures consistency, even when different workers or shifts are involved. It also supports the introduction of new model variants or upgraded parts, as digital updates can be rolled out instantly across the entire facility. But the factory's brain doesn't stop at the workstation level. Scania's facilities are organized using advanced logistics and material replenishment systems. These include just-in-time and just-in-sequence delivery models. In the GT approach, components arrive at the assembly line exactly when needed, reducing on-site inventory and waste. JIS takes this a step further by ensuring that parts not only arrive on time, but in the exact order the assembly line requires them, matching the customer-specific build schedule. To make this possible, Scania utilizes autonomous guided vehicles and collaborative robots, also known as cobots. AGVs are programmed to navigate specific paths throughout the facility, transporting parts, kits, and tools from storage to workstations. These mobile units are equipped with obstacle detection sensors and onboard computers, allowing them to safely navigate busy factory environments and prioritize urgent deliveries. Cobots, on the other hand, work directly alongside human operators. They handle tasks like component positioning, torque application, and small part assembly. Because cobots are designed to operate safely around people, they can perform repetitive precision tasks while allowing human workers to focus on complex decision-making and quality assessments. One of the most advanced implementations of lean philosophy at Scania is its digital twin system. This virtual representation of the entire truck assembly process allows engineers and planners to simulate workflows, test layout changes, and even trial new product designs in a fully digital environment before committing changes to the physical factory floor. These simulations integrate real-world production data, making them incredibly accurate and predictive. Before a new model is introduced, it is built and validated in this digital environment, ensuring the tools, workstations, and instructions are perfectly prepared for real-world production. The importance of training and workforce development cannot be overstated in this high-performance environment. New employees go through comprehensive onboarding programs, including virtual reality training simulations, where they practice assembly techniques and safety procedures in a risk-free setting. More experienced workers have access to continuing education through Scania's in-house training academy, which covers topics such as electronics diagnostics, sustainability practices, robotics programming, and leadership development. These programs ensure that Scania's workforce remains adaptive, skilled, and deeply connected to the company's long-term goals. Scania's commitment to sustainability extends well beyond the trucks it produces. It's embedded in the very operations of its factories. Each manufacturing site is governed by a green production strategy, which includes aggressive targets for energy efficiency, waste reduction, and carbon neutrality. Solar panels line the roofs of production buildings, and in several sites, geothermal energy or district heating is used to manage interior climate control with minimal environmental impact. Water used in paint shops and testing areas is filtered and recirculated using closed-loop systems, reducing freshwater usage dramatically. Waste from steel stamping, machining, and welding operations is meticulously sorted and sent back to steel suppliers for recycling, creating a circular materials economy. Even the packaging used for inbound components is standardized and reusable. Suppliers ship parts in containers that are returned, cleaned, and reused repeatedly. Scania's internal logistics fleet, used to move materials between factory sites and distribution hubs, now includes electric trucks and vehicles powered by biofuels, reducing the carbon footprint of interfacility transport. Each of these sustainability initiatives is audited and quantified, with progress reported in annual sustainability disclosures. The factories themselves are certified to international standards such as ISO 14001 for environmental management and ISO 50001 for energy management. ensuring that improvements are not only achieved but institutionalized. These practices aren't just good for the planet, they're good for production. Energy-efficient lighting, heat recovery systems, and smart building automation lower operating costs, which ultimately contribute to Scania's competitive advantage in manufacturing. Moreover, by reducing the environmental footprint of its operations, Scania aligns itself with the increasingly stringent regulatory demands in global markets, ensuring compliance without last-minute adaptation or retrofitting. But lean and green aren't the whole story. Scania also embraces operational transparency and external collaboration. Factory tours are not uncommon, not just for public relations, but for academic, industrial, and supply chain partners. These visits are carefully choreographed but open in intent, demonstrating Scania's willingness to share best practices and invite scrutiny. Likewise, feedback from suppliers, service technicians, and even end users is fed back into the production process. If a common failure mode or service complaint emerges from the field, engineers collaborate directly with line workers to trace root causes and implement corrections, sometimes within days. This culture of bottom-up innovation is rare in large-scale manufacturing, but thrives at Scania. Workers are encouraged to submit improvement suggestions, known internally as yellow cards, through a structured feedback mechanism. These ideas can range from tool redesigns and safety enhancements to procedural changes that save time or reduce fatigue. Implemented ideas are celebrated in team meetings, and successful contributors are rewarded not just with recognition, but often with career advancement opportunities. The ultimate outcome of all this is a manufacturing operation that is resilient, adaptable, and deeply human-centric, despite the heavy use of automation and digital systems. Each truck, though shaped by machines and moved by algorithms, bears the unseen fingerprints of hundreds of skilled individuals who have each left a mark on its creation. It is a deeply collaborative process where man and machine act not in opposition, but in orchestration. The creation of a Volkswagen Golf, one of the most iconic hatchbacks in automotive history, begins long before any metal is stamped or bolts are torqued. To truly appreciate the intricacy and precision of its manufacturing, we need to understand that this process represents the culmination of decades of engineering refinement, logistical coordination, and factory automation. It is not merely the assembly of components, but the orchestration of thousands of interdependent systems working in harmony, each with a dedicated role in transforming raw materials into a vehicle ready to roll off the line and onto the world's roads. The process begins at the heart of the operation, the Volkswagen manufacturing plant. One of the most famous Golf production facilities is located in Wolfsburg, Germany, where massive halls the size of several football fields stretch out in every direction. The atmosphere inside is clinical, controlled, and buzzing with quiet energy. Contrary to what one might expect, these spaces are not chaotic or deafening. They are meticulously organized, highly automated environments where human expertise collaborates with robotic precision to produce each vehicle to exacting standards. The first chapter in the physical birth of a Golf begins with the fabrication of the car's body shell. This process is commonly referred to as body in white, and it involves the welding and joining of raw sheet metal components that form the structural skeleton of the vehicle. These metal sheets typically arrive at the factory in pre-cut and coiled form, having been sourced from steel and aluminum suppliers who produce automotive-grade alloys with specific mechanical properties such as tensile strength, corrosion resistance, and energy absorption. Volkswagen has stringent quality controls on these materials, inspecting incoming shipments with laser scanners, chemical analysis equipment, and tensile testing machines to ensure that every roll meets the necessary specifications for forming and crash safety. Once approved, the metal sheets are uncoiled and fed into gigantic press machines, many stories tall, in what is known as the stamping area. These presses are a marvel in themselves, each capable of exerting thousands of tons of pressure. Using a combination of progressive and transfer dies, massive steel molds engineered to exact tolerances, these machines punch, bend, and form individual components like doors, hoods, roofs, floor panels, and side frames. Each die can weigh up to 40 tons and requires highly precise installation. The press line operates with the rhythmic certainty of a mechanical heartbeat, with each panel ejected onto a conveyor system that ferries it toward the next phase of production. From here, the stamped panels enter the body shop. This area is perhaps the most robot-dominated zone of the entire plant. Hundreds of robotic arms, painted in Volkswagen's signature orange or yellow, perform an intricately choreographed ballet of spot welding, laser welding, and riveting. These robots are guided by 3D coordinate programming and vision systems that allow them to make microscopic adjustments in real time. Their work is critical, as the dimensional accuracy of the welded body frame dictates how well later components, like the drivetrain and interior modules, will fit. The vehicle begins to take shape as floor panels are married with the side structures. Roofs are laser welded into place, and reinforcement beams are added to strengthen key impact zones. The welding robots are just one part of this highly automated process. In certain sections, human operators are still essential, particularly for tasks requiring dexterity, visual inspection, or adaptation to model variants. At these stations, workers equipped with pneumatic tools and ergonomic lifts work alongside the robots to install structural reinforcements, apply bonding agents, or verify alignment with laser-calibrated measurement systems. Every completed body shell is then run through a geometric measurement tunnel, where a series of cameras and lasers scan the surface down to the sub-millimeter level, ensuring that each vehicle conforms precisely to Volkswagen's quality blueprint. Once the body-in-white structure is completed and quality verified, the next transformative phase begins, the painting process. But before any color is applied, the raw metal body must be prepared to resist corrosion and adhere properly to the paint layers. The shell first passes through a cleaning and pre-treatment bath, typically involving a series of immersion tanks where it is cleaned of oils, particulates, and oxidation. This is followed by a process known as cathodic electrocoating, or e-coating. Here, the entire body is submerged in an electrically charged bath containing anti-corrosion primer particles. A low voltage current causes the primer to be drawn onto every metal surface, even inside closed box sections, providing complete and uniform protection. After e-coating, the body is dried in a curing oven and then transferred into the paint booths. These clean rooms are maintained at highly controlled temperature, humidity, and dust levels. The next steps involve the application of a primer layer, base coat, and clear coat, each sprayed using high-precision rotary atomizers. Robots again take the lead here, moving with fluid, sweeping motions to ensure a uniform paint film. Each coat is flash-dried between applications, and the final clear coat is cured in another high-temperature oven. Color accuracy and surface quality are assessed by specially trained technicians, often under special light tunnels that reveal even the most subtle defects or inconsistencies in the paint finish. With the painted body now cooled and cured, it proceeds to the marriage with the mechanical underpinnings, the powertrain, suspension, and chassis components. This phase marks the beginning of the general assembly process, which is one of the most logistically complex and human-involved areas of the plant. The painted body is mounted onto a continuously moving conveyor line known as the assembly line or production line, and begins its journey through a sequence of stations, each responsible for a specific set of tasks. One of the first major milestones on this line is the marriage station. Here, the body shell is carefully lowered onto a pre-assembled chassis, which includes the engine, transmission, front and rear axles, brake lines, fuel system, and other underbody modules. This process is performed using automated lifting gantries equipped with positioning sensors and torque control systems, ensuring that every bolt, mount, and fastener is attached with the correct torque specification. At this stage, precision is paramount. The alignment of engine mounts, suspension geometry, and drivetrain clearances are all verified using computer-aided fixtures and sensor feedback systems. As the car progresses down the line, workers and robots alternate in adding increasingly complex subsystems. Wiring harnesses, which have been pre-assembled in a separate part of the plant, are routed through the vehicle's interior and connected to key modules. These harnesses are essentially the vehicle's nervous system, containing hundreds of electrical wires that link sensors, control units, lighting, safety systems, and infotainment components. Routing these bundles accurately and securing them with clips, grommets, and tie wraps is both an art and a science, requiring a balance between accessibility, safety, and electromagnetic shielding. Following this, the interior components begin to enter the scene. Dashboards, HVAC units, center consoles, and infotainment displays are installed using guided insertion tools and laser alignment rigs. The seats, which are often built in a just-in-time fashion by a nearby supplier, are delivered directly to the line and bolted in place using high-torque pneumatic tools. Throughout this process, every module is scanned with a barcode reader to ensure traceability. This level of digital tracking allows Volkswagen to log the exact batch, supplier, and assembly timestamp for every major component, creating a complete digital twin of the vehicle's production history. By this point, the Golf has become instantly recognizable, with its iconic silhouette now cloaked in paint and outfitted with much of its interior. However, many critical systems have yet to be tested or activated. That next phase, electrical testing, fluid filling, and calibration, marks a turning point in the assembly process, transitioning the Golf from a mechanical object to a functioning machine. As the Volkswagen Golf continues its progression down the general assembly line, it begins to cross into one of the most critical sections of production: system initialization and functional testing. This stage transforms the vehicle from a silent shell into an electrically alive machine. It is here that the electronic control units, or ECUs, are first brought online. These digital brains govern virtually every function in the vehicle, from fuel injection timing and anti-lock braking response to climate control algorithms and sensor-based driver assistance systems. The Golf contains dozens of these ECUs, each responsible for different subsystems, and all interconnected through a series of high-speed data buses such as CAN, L-Line, and FlexRay. Before any electrical current is sent through the system, technicians connect the vehicle to a centralized factory diagnostic interface via a port located under the dashboard. The same OBD port later used by service technicians and inspection facilities. Using specialized software, factory workers upload the correct firmware and configuration data into the ECUs. This process is not merely about flashing software. It's about synchronizing every system to the specific build of that vehicle. Variables like engine type, transmission variant, lighting package, regional compliance requirements, and customer-selected options all influence how the ECUs behave. This digital handshake ensures the car will operate correctly and meet both performance and regulatory expectations. Once the ECUs are initialized, the next step is electrical verification. Automated test rigs are used to check that every connection, sensor, and actuator is functioning correctly. These rigs apply voltage and resistance checks through the wiring harness, lighting systems, and control modules. Even minor faults, such as an improperly seated connector or excessive resistance in a wire, are immediately flagged by the system. Any detected issues cause the car to be diverted from the main line to a specialized diagnostic bay where trained technicians perform pinpoint troubleshooting and rework, ensuring that no electrical faults go undetected. Parallel to the electrical system bring-up, the vehicle also receives its initial fill of operational fluids. These include engine oil, coolant, brake fluid, transmission fluid, power steering fluid if hydraulic, and in some cases, refrigerant for the air conditioning system. The filling process is performed by robotic dispensing arms that are pre-programmed to deliver the precise volume and type of fluid required for each model. Flow meters, pressure sensors, and digital records ensure absolute consistency and prevent underfilling or contamination. The fuel tank is also filled with a small amount of test fuel, typically around 5 to 10 liters, sufficient for initial startup, emissions testing, and short-range driving tests later in the process. After fluid filling, one of the most dramatic moments in the assembly process occurs: the engine start. This is not done casually, nor is it done without extensive prior checks. Once all systems are confirmed ready, a technician activates the ignition via the factory diagnostic system or a standard key fob, causing the engine to turn over for the first time. Sensors throughout the vehicle immediately begin transmitting data: engine RPM, oil pressure, coolant temperature, voltage levels, and emission sensor feedback, all of which are monitored live by quality assurance software. If the engine does not start within a certain time window, or if any critical values fall outside the permissible range, the vehicle is automatically flagged for further inspection. Assuming a successful startup, the next phase involves dynamic system checks. These include actuating key mechanical subsystems to ensure proper functionality. The steering is rotated lock to lock to test assist levels and detect any binding. The brakes are pressurized to confirm pedal feel and hydraulic integrity. The transmission is cycled through its gears, with automatic models shifting through each range while stationary, and manual models undergoing clutch engagement tests. Additional functions like power windows, central locking, infotainment screens, headlight alignment, and mirror adjustments are also verified at this stage. All of these checks are conducted on the moving assembly line or at dedicated inspection stations known as end-of-line testers. These stations are equipped with rollers, sensors, cameras, and feedback terminals that allow technicians to observe live data streams. If a vehicle passes all of these checks, it is allowed to proceed to the next major step: wheel mounting and torque application. At this point, the Golf receives its wheels and tires, which have been assembled and balanced in a separate part of the plant. Tire suppliers often work in close partnership with the assembly plant, sometimes even maintaining satellite facilities on site to deliver tires in real time according to the production sequence. The wheels are mounted using robotic arms equipped with torque sensing screwdrivers. These tools are programmed with model-specific torque settings and follow a defined tightening sequence to ensure that every lug nut is fastened uniformly, reducing the risk of vibration or uneven stress on the brake rotors. After wheel installation, the vehicle is lowered off its assembly jigs and finally touches the ground under its own weight. This moment, often called first contact, marks the vehicle's readiness for dynamic testing. It is now fully assembled, fully functional, and ready to move under its own power. But production does not end here. The vehicle is then driven, slowly and under tight controls, to the next area of the plant: the rolling road test bench, also known as the dynamometer station. Here, the car is placed onto a set of rollers that simulate driving conditions while keeping the vehicle stationary. The purpose of this test is to perform a full-spectrum functional evaluation under load. The vehicle is accelerated, decelerated, and driven at varying speeds while sensors record engine performance, emissions output, braking effectiveness, and drivetrain behavior. Advanced vision systems check headlight aim and beam shape. Microphones measure cabin noise under acceleration. Even the wiper system is tested using artificial rainfall nozzles while the car is driven at simulated speeds. If any aspect of this test fails to meet Volkswagen's internal benchmarks, the car is again pulled from the line and sent to a rework zone. Here, highly trained specialists diagnose and resolve the issue, whether it be a misaligned sensor, a software glitch, or an out-of-spec component. Vehicles cannot proceed to final inspection until they achieve a perfect score on the dynamometer test. Following this dynamic validation, the car enters the final quality inspection area. This zone is brightly lit and staffed with quality control inspectors who perform a visual and tactile examination of every surface, seam, and feature. Paintwork is scrutinized under color-correct lighting to detect any blemishes, orange peel, or dust inclusions. Door gaps and panel alignment are measured with precision gauges. Interior materials are checked for fit, finish, and correct placement. Inspectors open every door, operate every switch, and sit in the car to check for rattles, uneven padding, or installation errors. This is often the first time someone interacts with the Golf as a complete product, and every detail matters. Once the vehicle passes its final inspection, a protective wrap is applied to its most vulnerable surfaces, typically the hood, roof, mirrors, and door edges, to prevent damage during transport. Barcodes and shipping labels are affixed, and the vehicle is driven to the logistics yard, where it joins a massive fleet of completed Golfs waiting for shipment. These yards are organized with incredible precision, with each car's location digitally tracked for efficient loading onto transport trucks or rail cars. While this marks the end of the physical assembly process within the factory walls, the story of each Golf is far from over. It now enters the distribution and logistics phase, a sprawling global network designed to deliver each vehicle to its final destination as quickly and safely as possible. But that segment of the journey involves a separate layer of logistical planning, international coordination, and dealership preparation, all of which merit a detailed explanation of their own. The freshly assembled Volkswagen Golf, now cloaked in its protective transport films and validated through layers of mechanical, electrical, and aesthetic inspections, begins its transition out of the factory environment and into the broader world. This stage, the post-production logistics and distribution process, is a sophisticated dance of real-time tracking, intermodal transportation, and region-specific compliance, all of which are critical to ensuring that each vehicle reaches the correct dealer in the correct configuration and in pristine condition. After final inspection, the Golf is driven from the assembly line to the Vehicle Logistics Center, often located adjacent to the main manufacturing facility. Here, trained drivers guide the vehicles along designated internal roads, maintaining low speeds and following strictly mapped routes to avoid cross-contamination or accidental damage. At the staging yard, vehicles are sorted based on destination markets, production variants, and transport mode. Some will head to domestic dealerships via truck, while others will be loaded onto trains for long-haul land journeys. For global markets, many Golfs are prepared for shipping by sea, making their way to port via specialized car-carrying rail networks. Before any Golf leaves the staging yard, a final scan is performed. Using handheld barcode scanners or RFID readers, workers verify the vehicle's unique VIN, vehicle identification number, against the factory's production records. This cross-referencing ensures that the car has passed all necessary quality gates, has been matched with the correct transportation order, and is headed to the appropriate regional hub. Additionally, certain destination countries require extra compliance steps before a vehicle can legally enter or be registered, such as emissions documentation, safety certification, or region-specific firmware updates to the vehicle's ECUs. These requirements are embedded into the logistics planning software, and vehicles are automatically routed to compliance zones where technicians apply the necessary updates or decals before departure. Once verified and queued, the Golf is prepared for loading onto a transport carrier. For truck transport, specialized vehicle haulers equipped with multi-level ramps are used. These carriers are engineered to accommodate various vehicle sizes while maximizing capacity and maintaining balance for road stability. Loading is conducted with extreme care. Each car is driven up ramps and secured using wheel straps, chocks, or integrated platform locks that prevent movement during transport. Drivers are trained not only in vehicle handling, but also in load balancing, ensuring that the distribution of weight across the trailer complies with legal road limits and mechanical tolerances. For long-distance rail transport, the Golf is moved onto enclosed or open-sided car transport wagons. These wagons can hold up to a dozen vehicles per unit and are designed to withstand the rigors of long-haul journeys across multiple climate zones. Rail is favoured for its cost efficiency and environmental impact, particularly for routes within Europe, where dense rail infrastructure allows cars to be delivered to regional distribution centres with minimal handling. Once the vehicles reach their destination hubs, often located just outside major cities, they are transferred to final mile delivery trucks that ferry them to individual dealerships. When the Golf is destined for international markets outside of Europe, such as North America, Asia, or Australia, it must be transported by sea. This requires loading the vehicles onto large roll-on/roll-off cargo vessels, also known as ro-ro ships. These enormous ships are essentially floating multi-story parking garages, capable of holding thousands of vehicles at once. At the port terminal, cars are driven aboard by logistics personnel who work under tight schedules to fill each ship efficiently. Vehicles are parked according to a precise digital manifest, which maps each car's location by deck, row, and position for accurate unloading at the destination port. Ro-ro shipping requires a high level of environmental control. Vessels are designed to maintain safe humidity levels, minimize exposure to salt air, and prevent the movement of cars in rough seas through a system of tie-down points and loading jacks. Once the vehicle arrives in its destination country, it goes through a process known as port processing. This includes customs clearance, regulatory inspections, and any market-specific modifications. Depending on the country, this might involve the installation of alternative language infotainment software, the addition of local safety equipment like fire extinguishers or first aid kits, or the application of region-specific emblems and badges. Vehicles are once again inspected for transport-related damage, cleaned, and detailed before being sent to the dealership. But while distribution is an essential part of the car's journey, it is merely the final chapter in the broader industrial narrative. To truly understand the full scope of how a Volkswagen Golf comes to be, we must look beyond the visible car to the invisible infrastructure that supports its manufacture, the supplier network, component fabrication, and just-in-time logistics that converge at the assembly plant, like veins feeding into a living heart. Every Golf is made up of more than 30,000 individual parts, many of which are produced not by Volkswagen directly, but by a web of Tier 1 and Tier 2 suppliers across the globe. These include suppliers specializing in electronics, seats, glass, tires, injection molded plastics, turbochargers, radiators, axles, and much more. These companies operate under strict quality and timing requirements, often working within a just-in-sequence framework. This means that not only must the parts arrive just in time to avoid stockpiling or shortages, but they must also arrive in the exact order in which they are needed on the line. To enable this, Volkswagen uses a combination of supplier parks, regional distribution centers, and digital planning tools that forecast production demand down to the minute. Many of these suppliers operate satellite facilities on or near the Volkswagen campus itself. These microfactories are tightly integrated into the main production loop. For instance, a seat supplier may receive a digital order moments after a car body is painted and matched to a particular trim level. Within hours, the seat is built, quality checked, and delivered to the assembly line just as the car arrives at the station where it will be installed. The just-in-time system dramatically increases efficiency and reduces warehousing costs, but it also demands precision and resilience. Any disruption in the supply chain, whether due to weather, labor issues, or global events, can ripple across the production schedule. To manage this complexity, Volkswagen employs advanced manufacturing execution systems and enterprise resource planning software that communicate with suppliers, forecast demand, and adjust schedules in real time. Each supplier must adhere to predefined quality protocols, including statistical process control, failure mode analysis, and traceability documentation, which are routinely audited by Volkswagen's internal teams. On the component level, many key parts are manufactured using highly specialized processes before they ever reach the main assembly line. Take, for example, the engine, the mechanical heart of the Golf. Engine blocks begin their life as raw aluminum or cast iron, melted and poured into precision molds using high-pressure casting methods. Once solidified and cooled, the blocks are machined using CNC equipment that drills, hones, and surfaces the bores and mating faces to tolerances often measured in microns. Crankshafts, camshafts, pistons, and cylinder heads undergo similar processes, each passing through multiple heat treatment, grinding, and quality inspection stages before final assembly. The completed engine is then mated with its transmission, tested on a cold bench, a fixture that simulates operation without fuel or combustion, and sent to the main production hall. There, it joins the sequence of drivetrain assemblies that will eventually meet their respective body shells on the marriage line. Similarly, high-tech components like digital dashboards, ADAS sensors, and infotainment head units are built and tested in cleanroom environments to prevent contamination or electrostatic damage. These electronic assemblies are subjected to functional tests, environmental stress simulations, and firmware updates before being sent to the main line. At the plant level, all of these moving parts, mechanical, logistical, and digital, converge into what is often described as a cyber-physical production system. Assembly lines are increasingly governed by AI-enhanced predictive analytics, machine learning algorithms that forecast wear on machinery, and autonomous material handling vehicles that navigate factory floors using LiDAR and GPS. Real-time dashboards allow factory managers to monitor production flow, equipment uptime, part inventories, and worker ergonomics from centralized control centers. Robots, collaborative arms known as cobots, and human workers form a hybrid workforce that constantly adapts to changes in demand, variant complexity, or technological updates. All of this results in a manufacturing ecosystem that is as complex and finely tuned as the vehicles it produces. The Volkswagen Golf, which might appear to the average buyer as a simple compact hatchback, is in reality the output of a global network of suppliers, engineers, robots, and logisticians working in concert with millisecond-level precision. It is a product born of thousands of hands and millions of decisions, every one of them contributing to the moment when the car's engine starts for the first time, the headlights blink to life, and it begins its journey toward the showroom floor. As the story of the Volkswagen Golf continues within the factory walls, we now shift focus to the critical yet often overlooked phase that follows the assembly and functional testing of the physical vehicle. Final calibration, detailed software programming, and human-centered quality control measures that ensure not just mechanical soundness, but also driving experience fidelity, safety compliance, and brand consistency. This stage marks the final opportunity for engineers and technicians to refine the car's personality, the way it feels, sounds, and responds before it ever reaches a dealership. Once the vehicle passes its rolling road test, electrical verification, and cosmetic inspections, it enters what's referred to in modern manufacturing as the calibration and personalization loop. Here, technicians interface with the vehicle's multiple electronic control units, upwards of 50 in many Golf variants, to fine-tune parameters such as steering weight, throttle response, transmission shift points, air conditioning behavior, and even ambient lighting modes. Although these parameters are based on predefined model profiles, small adjustments are often needed to account for tolerances in component performance, environmental conditions, and the specific variant configuration of the vehicle. This process uses a digital toolchain, often referred to as a centralized vehicle configuration system. The technician connects a specialized programming console to the vehicle's onboard diagnostics port. Through this interface, the system retrieves the vehicle's build sheet, a digital summary of every major component, trim level, engine type, and region-specific setting installed during production. Based on this, the technician downloads the relevant firmware packages and configuration profiles from a secure Volkswagen server. These files include calibrations for dynamic systems like ESC, lane keeping assistance, adaptive cruise control, and the steering rack's servo control logic. The software installation itself is performed with high redundancy and validation steps. Each module receives a cryptographic checksum, ensuring the integrity of the code after download. The system then runs a diagnostic sweep, verifying that all ECUs are correctly communicating across the vehicle's CAN and LN bus architecture. Should any module fail to respond or report a checksum mismatch, the vehicle is flagged and removed from the main line for specialized reprogramming in a secure rework area. This level of rigor is necessary, not only to ensure reliability and drivability, but also because these software systems control functions directly linked to passenger safety. Following calibration, the vehicle passes through a sequence of human-led evaluations known internally as sensory audits. In a world increasingly governed by automated inspection and robotic precision, this human touch remains indispensable. Sensory audit teams, often composed of master technicians and experienced inspectors, evaluate things that machines cannot easily quantify. They listen for rattles or unexpected noises while operating various components, apply gentle force to test the feel of buttons and switches, and run their hands along upholstery seams to detect imperfections in fit or material finish. These teams test the firmness of seat padding, assess the resistance in climate control knobs, and verify the damping in the glove box lid's opening motion. This inspection process is not random. Each inspector follows a detailed checklist created for the Golf's specific variant, whether it's a base TSI model or a performance-oriented GTI. Every tactile point of interaction with the driver or passenger is scrutinized. The sound of the door closing, the feedback of the turn signal stalk, the clarity of the infotainment screen. Even the air vents are examined for smooth adjustability and structural integrity. These subtle, almost imperceptible qualities play a vital role in shaping customer perception. They influence whether a driver describes the Golf as solid, refined, or thoughtfully engineered. And Volkswagen knows that these sensory markers directly translate to brand loyalty. Parallel to the sensory audit is a final high-pressure water test. Here, the vehicle is driven into a sealed chamber where it is subjected to a simulated rainstorm, complete with directed nozzles spraying water at high pressure from multiple angles. The goal is to identify leaks around door seals, windshield bonds, taillights, and underbody grommets. As the water jets barrage the vehicle, sensors inside the cabin monitor for moisture ingress, while technicians inspect areas with flashlights and absorbent strips to detect even minute amounts of seepage. Any vehicle that fails this test is returned to a specialized sealing and bonding repair zone where issues are addressed before retesting. Once these final inspections are complete, the vehicle is officially released from production. However, in a modern Volkswagen plant, this release is also the beginning of a data-rich archival process. A complete digital profile of the vehicle, from every torque specification logged during assembly, to the paint batch number, to the firmware version of the braking system, is uploaded to a central database. This digital twin acts as a permanent reference for the vehicle throughout its service life. If a recall or service bulletin is ever issued in the future, this record allows Volkswagen to identify not only which vehicles are affected, but precisely what components or subsystems were installed and when. It is also worth noting that many Golf variants are produced with advanced driver assistance systems, which require a final calibration procedure using sophisticated optical targeting tools. This is especially critical for features like lane keeping assistance, traffic sign recognition, autonomous emergency braking, and adaptive cruise control, which rely on a front-facing camera, radar sensors, and sometimes LiDAR. These sensors must be calibrated in relation to the car's central axis, suspension height, and tire circumference. The calibration process is performed in a controlled bay using visual markers, checkerboard targets, and reference panels, positioned at known distances. Specialized software then guides the technician through alignment adjustments and performs a verification routine, simulating input data to test the system's reactions. The factory also considers the growing importance of software updates throughout a vehicle's lifecycle. Increasingly, Golf models are being built with over-the-air update capabilities. This means that certain vehicle functions can be improved or corrected remotely without visiting a dealership. To enable this, each vehicle must be registered with Volkswagen's secure update server and fitted with a telematics control unit capable of handling encrypted data downloads. Before leaving the plant, the vehicle undergoes a brief connectivity test using a private cellular or Wi-Fi network. This ensures that the vehicle can receive updates in the field and that the security keys assigned during factory programming are valid and authenticated. Another major focus of final stage production, particularly in recent years, is environmental sustainability. Volkswagen has implemented comprehensive measures to reduce the ecological footprint of Golf manufacturing. For example, paint shops, traditionally among the most energy-intensive and pollutant-heavy parts of vehicle production, now use water-based paints and advanced overspray capture systems to reduce volatile organic compound emissions. Waste heat from ovens and drying tunnels is recovered and recycled into the factory's climate system. Water used in the electrocoating and wash booths is treated on-site and reused in a closed-loop system. Powering the factory itself is a growing area of environmental emphasis. Many of the plants where the Golf is manufactured have transitioned to renewable energy sources, such as wind or hydroelectric power. In Wolfsburg, for instance, Volkswagen has partnered with regional utilities to supply the production lines with green electricity. Additionally, automated lighting, motion sensors, and energy-efficient drive systems on robots and conveyors contribute to reduced overall consumption. These investments not only lower the per-vehicle carbon output, but also align with Volkswagen Group's broader Way to Zero strategy, a commitment to climate-neutral mobility and carbon-neutral production by 2050. Within the plant, materials management is handled with sustainability in mind as well. Steel and aluminum scrap generated during stamping operations are carefully sorted, compressed, and sent to recycling centers, some of which are reintegrated back into the supply chain. Plastics from production offcuts or rejected trim parts are ground down and reused in non-visible components. Even packaging materials used to deliver parts, such as crates, dividers, and protective films, are tracked and returned to suppliers in a closed-loop logistics model. What makes the Volkswagen Golf's production so remarkable is not just the car itself, but the systems, philosophies, and technological ecosystems that produce it. Each vehicle embodies the cumulative effort of thousands of hours of engineering, years of supplier relationships, terabytes of design simulations, and millions of precisely orchestrated manufacturing movements. What rolls off the line is not a standalone product, but the physical representation of a global, highly optimized industrial organism. One designed to balance quality, efficiency, innovation, and sustainability in every nut, panel, circuit, and drop of fuel or electricity it consumes. As we move deeper into the Volkswagen Golf's manufacturing story, we begin to explore the systems behind the systems, the cutting-edge technologies and organizational strategies that elevate Golf production beyond traditional automotive assembly. Much of this innovation centers around Volkswagen's use of modular platforms, intelligent factory automation, and advanced data analytics, all of which have transformed not just how a Golf is made, but how efficiently, flexibly, and sustainably it can be produced, alongside a range of other vehicle models. At the core of this evolution is Volkswagen's MQB platform, short for Modulare Kurbaukasten, which translates to Modular Transverse Matrix. Introduced in the early 2010s, this platform underpins not only the Golf, but also a wide range of vehicles across Volkswagen Group's brands, including the Audi A3, Seat Leon, and Skoda Octavia. The brilliance of the MQB platform lies in its standardized architecture. Critical hard points, such as the position of the engine, the distance between pedals and front axle, and mounting locations for crash structures, are fixed across models, while allowing flexible variation in wheelbase, track width, and body style. This enables massive economies of scale and allows the Wolfsburg plant, among others, to produce multiple models on a single line with minimal retooling. In practice, this means that a Golf might be built on the same line as a Tiguan or a Touran, using many of the same robotic stations, fastening tools, and software configurations. Tooling carts, parts bins, and robotic arms are designed with adaptability in mind. Instead of having separate jigs for each model, multifunctional fixtures and programmable robots detect the incoming body type via RFID tags or QR codes and adjust themselves in real time. A welding robot, for example, might apply different sequences or torque levels, depending on whether it is working on a Golf hatchback or a longer wheelbase estate model, all without human intervention. This production flexibility is supported by a sophisticated manufacturing execution system, a digital nervous system that tracks every car's status as it moves through the factory. Each vehicle is assigned a digital build order, stored in a centralized database and updated in real time. This build order contains detailed instructions for every station: which components to install, what software to flash, how to calibrate sensors, and which quality checks to perform. At each workstation, screens display the relevant data for the technician or robot, and barcode or RFID scanners confirm that the correct parts are being used before the system allows the job to proceed. The use of artificial intelligence and machine learning is increasingly embedded into this ecosystem. For instance, predictive maintenance systems monitor vibration, temperature, and performance data from thousands of robots, conveyors, and tools in real time. If a welding robot's arm begins to show early signs of wear, even imperceptible to human operators, the AI flags the issue and schedules preventative maintenance before failure can occur. This predictive approach significantly reduces downtime and helps maintain the tight production cadence that modern car manufacturing demands. Another area where AI plays a pivotal role is in vision systems and quality control. High-resolution cameras paired with deep learning algorithms are used throughout the assembly and inspection processes. These systems are trained on thousands of images to identify correct panel alignment, paint consistency, weld seam quality, and even minute cosmetic defects. In the paint shop, for example, the system can detect a single dust particle trapped in a clear coat, then alert technicians to isolate the cause, whether it's an air filtration issue, static charge on the body panel, or improper cleaning upstream. These insights are logged and used to refine both the hardware and the process over time, feeding back into a continuous improvement loop. But AI is not just about machines replacing human oversight, it's about augmenting human decision-making. In interior assembly, where more variation exists due to trim-level complexity, workers are assisted by augmented reality headsets that project assembly instructions directly into their field of view. These AR systems highlight where each clip, fastener, or electrical connector should go and can overlay 3D models of correct placements onto the physical work area. If the system detects a potential mismatch, such as a left-hand drive HVAC control unit being installed in a right-hand drive model, it alerts the worker before the part is fully installed. This not only reduces errors, but empowers technicians to handle more complex tasks without relying solely on memory or printed documentation. All of these advancements contribute to a concept Volkswagen refers to as smart production, an overarching philosophy that treats the factory not as a static facility, but as a living, evolving system. This philosophy is particularly evident in how Volkswagen manages its energy consumption, materials flow, and human ergonomics. For example, autonomous guided vehicles have largely replaced traditional forklifts and trolleys in many areas of the Golf's production. These AGVs navigate using a combination of magnetic strips, LiDAR, and real-time mapping, delivering parts from storage zones to the assembly line on demand. This reduces congestion, minimizes human error in part selection, and allows the line to adapt more fluidly to shifting production priorities. From an energy standpoint, smart production integrates intelligent building management systems that adjust heating, cooling, and lighting based on real-time occupancy and environmental data. Robots enter standby mode when idle for more than a few seconds. Compressed air systems, traditionally one of the most energy-intensive parts of any industrial plant, are monitored by AI that optimizes pressure delivery to exactly what is needed, exactly where it is needed, with zero excess. These micro-optimizations, when multiplied across thousands of systems and millions of cycles per year, contribute to measurable gains in sustainability. Ergonomics and human factors are also key to this philosophy. Every workstation on the Golf assembly line is designed to reduce strain, fatigue, and injury. Adjustable platforms allow workers to bring the vehicle to an optimal height depending on the task. Overhead assist arms support the weight of heavy tools, reducing the need for muscle force. Color-coded part trays, automatic torque wrenches, and real-time feedback screens help workers maintain quality while minimizing the mental load of memorizing dozens of process steps. Additionally, Volkswagen invests heavily in worker training, offering digital simulators, VR-based assembly previews, and rotating task assignments to improve skill versatility and maintain high morale. This combination of human-centered design and intelligent automation also allows the Golf production line to be highly responsive to changing market demands. If a sudden spike in orders for a particular trim level occurs, say the Golf GTI with a sunroof and adaptive suspension, the MES system can reprioritize the build queue, notify suppliers of increased part demand, and adjust the workstations along the line in real time. Robots recalibrate their movement patterns, AGVs update their delivery routes, and workers are presented with new instructions through their digital displays. What once would have required days or weeks of retooling now happens in hours, or in some cases, minutes. One of the most compelling outcomes of these systems is Volkswagen's ability to maintain quality parity across global production sites. Thanks to centralized data systems, a Golf built in Wolfsburg can be virtually identical in build quality and performance to one assembled in Puebla, Mexico, or Changchun, China. Volkswagen uses digital twins of its production equipment, virtual replicas that simulate and mirror real-world machines, to replicate best practices across all facilities. If a process optimization is discovered in one plant, such as a more efficient adhesive application method or a faster sensor calibration routine, that improvement can be tested digitally, validated, and then rolled out to other sites via secure updates to their MES software. All of these advancements are not just about building a better car. They're about building a better manufacturing system, one that is scalable, adaptable, and forward-compatible. This is especially important as the automotive industry transitions to electrification. The Golf, as of the latest generation, shares many of its production processes with Volkswagen's ID family of electric vehicles. While the ID.3 and ID.4 are built on a separate platform, MEB. The lessons learned from MQB production, including robot versatility, flexible logistics, and digital calibration, are directly transferable. In fact, many stations within the same factory can now switch between building a combustion engine Golf and an electric vehicle, with only minor tooling changes and software adjustments. Volkswagen's approach to production is ultimately one of modular intelligence, a blend of standardized hardware, reconfigurable software, and scalable systems that can evolve with the demands of new technologies, consumer preferences, and global regulatory changes. And in this sense, every Golf rolling off the line is not just a vehicle. It's a node in a vast, intelligent, and continually learning machine.